Okay, so I would like to welcome everyone to today's workshop, Introduction to Data Science for Biomedical Researchers. I would like to give a brief introduction before the actual workshop starts. My name is Jing Liu. I'm the Managing Director of the Michigan Institute for Data Science, or we call it MIDAS. I think I hope everybody can see my screen just fine. Okay, so for this particular audience, I think many of you have not been working with MIDAS much in the past. So I want to tell you a little bit about who we are and what we do. So MIDAS is the central component of the data science initiative that was started about 5 years ago at the university. Our mission is to strengthen University of Michigan's preeminence in data science and AI, to catalyze the transformative use of data science and AI in a wide range of disciplines to achieve lasting societal impact. I'm highlighting 3 phrases here on this slide to indicate that our responsibilities are to the university, to science, and to the society. Our leadership team includes Dr. H.V. Jagadish, who is the director and a professor in computer science and engineering, me, and 3 associate directors. Pamela Davis-Keene is the associate director who works closely with the social scientists on campus. Kayvan Najarian, who I will come back to, is the associate director who works closely with the biological science and biomedical and clinical science researchers on campus. Ivo Dinov is our associate director for education and training. Jag also works closely with the data scientists in the engineering and the arts disciplines on campus. So when we talk about data science and AI, we really talk about 3 main parts. One is the theoretical foundation. These are mostly math and statistics researchers who define the behavior of big data and what we can do with it. Then there are people like computer scientists and information scientists who translate the theory into tools and methods that we can apply to big data. Then we have a large number of disciplines that can use such tools and methods. On campus, we have plenty of all these people. MIDAS helps to bring these people together to form a truly interdisciplinary research community. So who are the data science community at Michigan and at MIDAS? These are researchers. MIDAS currently has about 350 faculty members from almost all schools and colleges at Ann Arbor campus, plus Dearborn and Flint campuses. About a third of them are involved in some way with biomedical and clinical research. We support their research, but more importantly, I would like to think about MIDAS as a platform for these researchers to make an impact on data science. So in a second, one of our staff members will put some links in the chat box. One of them is an application form to become an affiliate member of MIDAS. So you're welcome to fill out that form. We also want to talk with you and understand how we can support you and how we can let you use our platform. So you can email us, you can email me, you can email Kayvan. This afternoon at the networking session, I hope to talk with many of you as well. We also, in our community, we also have a staff data scientist network. And currently we have about more than 100 members from more than 60 research units. We also have more than 1,000 students in our network at undergraduate and graduate level. And we have more than 40 external partners. So how do we support research? We enable groundbreaking ideas through Ideas Hub, through fostering interdisciplinary collaborations. We provide resources such as pilot funding, access to data sets, supporting projects and proposals. And in the past 10 months or so, we've focused a lot on developing, together with the campus, guidelines and tools for reproducible data science. We help people improve their skills through various training, including today's workshop. And we offer a lot of data science events for the research community. In the chat, you'll see 2 upcoming events that I'll mention in a second. Here, I'm representing the supports that we have for investigators at various stages of research projects, from skill building and to when you build your ideas and your teams, to funding, to data acquisition, processing, and analysis, and dissemination. So this is just a different way of visualizing what support we provide to you. These are all on our website with much more details, and I would like to encourage you to explore. So the 2 upcoming events that I want to mention, one is a consortium for data scientists in training happening this Thursday and Friday, featuring speakers, graduate students, and postdocs from 26 universities. So this is a nice way to have a survey of the cutting edge data science research happening nationwide. In mid-November, we have our Data Science Symposium, which is the largest data science event on campus each year. We have some exciting keynotes and vision talks by faculty members. We also have 6 mini workshops, from introduction to Python programming, to scrubbing of sensitive data, using text data, especially clinical notes, agent-based modeling, processing of video data, and linkage for census data. And I highly encourage all of you to think about attending. I also want to mention a little bit of our role in education and external engagement, just because some of the audience members might find this interesting. Our education activities focus on enhancing students' research skills through real-world experience, career connections, and we also offer unique programs, including the Graduate Certificate Program and the Michigan Data Science Postdoctoral Fellows Program. We work with our external partners to both promote and enable responsible data science, and also to help our partners build capacity in data-driven decision-making. Through this process, we actually line up a lot of research projects and funding for both of our researchers and our students as well. I want to turn to Dr. Keyvan Najarian, who is the lead instructor today. So Keyvan is an associate director at Midas, as I just mentioned, and he's the point person for biomedical and clinical data science research on campus. He's a professor of computational medicine and bioinformatics, emergency medicine, and electrical engineering and computer science. He is also the director of the Biomedical and Clinical Informatics Lab and is the associate director for the Michigan Center for Integrative Research in Critical Care. Keyvan's research focuses on signal and image processing and machine learning methods to create computer-assisted clinical decision support systems that improve patient care and reduce the costs of healthcare. His lab also designs sensors to collect and analyze physiological signals and images. Clinical applications of his research include traumatic brain injuries, traumatic pelvic abdominal injuries, and hemorrhagic shock, cardiac arrest, and other critical care states. Keyvan collaborates extensively, truly extensively, with UVM and external researchers, both in academia and industry. He's also passionate about teaching data science. I think we're very fortunate that he was willing to design and teach this workshop and the upcoming bootcamp. Before I pass the mic to Kayvon, I also want to mention that James Walsh is the staff member at Midas who has been giving a lot of support to this workshop. If you guys have questions about the continuing medical education credits, if you have questions about logistics for networking, James is the guy. So I hope you enjoy today's workshop, and I'll see you at the networking session later in the afternoon. Kayvon?
Thank you very much, Jing. That was excellent, very nice introduction. So good morning. My name is Kayvon Najarian. Most of today you're stuck with me, so I will try to talk less and show more slides so that you can better see the contents. But while I'm doing that, I want to thank again Jing and James, who did basically 99% of all the things that you see today. So without their dedication to and contribution, would have been very difficult to design this workshop. So I hope that you all can see the slide. Good. So I'm going to start by introducing the instructors and saying a few things about the workshop. First thing I want to tell you is the plans that we have for this program. The whole training program is designed to give some introduction to data science, to people who are doing research in biomedical sciences. And we have created this training to have 3 parts in it. First part is the workshop that we have today. We talk about why we should do this and what are the benefits of that, who should take this, who should not take it, and what would be the content of the training, and who's teaching that, what other resources are available. That's what we're going to do today, and I will get back to the details of this later on. But then the second phase of this training would be a boot camp that happens sometime in summer of 2021. We haven't fixed the date exactly yet, but it will be soon announced. And that would be like a week of real training on data sciences. But then the third component, which happens in fall of 2021, is the bunch of follow-up meetings that people in this workshop, they learn about what they can do or what they cannot do if they take this like boot camp. Then once they get the boot camp, they get the training, then they need to do the biomedical research with some emphasis on data sciences. But what we have seen in the past is that these trainings happen, and after that there is no follow-up, and people who get this training, they don't know how to use it in real world, and after a while they just forget everything. We don't want this to happen, and because of that, we have the third phase, which is the follow-up meetings. I think once a month. We're planning to have it once a month, that we get all the participants again, like in a Friday afternoon or something. We get together and we talk about our experiences, the challenges that we have, and that would give us an opportunity to sort of follow up with individuals who need to, get more, guidance and help on data sciences, and help them actually use data science in their work. So without these 3 phases, I think the training would be not very helpful. Today is very important because we want to see who should actually participate in that and what would be the content of the training. So the title of the program says that this was designed for biomedical sciences, but in reality, the contents, many parts of this training program are actually, they can be used for any kind of disciplines. Like if you're in social sciences, if you're in other, like in even some types of engineering, or we are hoping that, and that, you know, we're moving towards that, the point that we create different versions of this training program for people with different disciplines. We wanted to start with biomedical sciences because, as Jing mentioned, 30% of the people who are involved in Midas, they're doing some sort of biomedical or biomedical related research. So it was the natural starting point for us. However, like I said, once we learn from this and we develop further content and specialized content towards other disciplines, hopefully we'll have similar things for other disciplines. Looking at the list of participants, or at least people who registered for this training, I saw people from, you know, not only medicine and dentistry and nursing and pharmacology, there are people from engineering, social sciences. So what I see is that maybe we, you know, even in this offering of the training program, we have, at least as the as long as the participants are concerned, we have a diverse sort of a spectrum of expertise you know, represented in the audience. So that would be hopefully, you know, a good start for such a training program. So let's see what are the goals of this workshop. First goal for this workshop is just introduce the instructors and speakers. And some of them, you already see them in the panel list. And we're gonna talk about what we're doing, who we are, and then discuss some ideas, how data science is typically often used in medicine and biology. We talk about some, you know, methodologies that people typically use in medicine, what are the type of applications that people use, and we talk about the opportunities and the challenges. If you're planning to use data science, you need to know what are the risks involved in that, and we go over that together. Then we talk about how a person whose career path is in clinical and biomedical sort of research, how they can use data science to, you know, to strengthen and like improve their likelihood of success. In other words, we want to see if you have this path towards, for example, clinical research, how data science can be added to give sort of an advantage and a competitive edge to the research, and distinguish your research from others who are doing purely clinical or biomedical work. We want to see how we can help our career by adding data science as a tool to the entire, you know, like research focus. And we're going to explain who can truly benefit from this training. And in order to understand who can truly benefit from this training, we're going to focus on who may not benefit much from this training. So you will see that when we discuss the people who are the best participants of this workshop and boot camp and follow-up meetings, you will see that my emphasis would be mostly on who won't be, you know, the best user of such a workshop, the cases that it may not be very helpful for you. Another goal is talking about, okay, so we talk about who can benefit, who can, like, you know, get into this training. And then we want to talk about what are the expectations that you can have when you're done with the training. What is it that is added to your skill set? What you can do? What level of expertise in data science you can expect from yourself once you graduate from this training program? And again, just like the previous step, my focus would be what not to expect from the program, because, you know, we're talking about 1 week of, you know, training in data sciences. There's a lot to be said about what not to expect from 1 week of training than what you can actually expect from it. So we want to clarify what are the skills and what level of a skill set you will have once the training set is training program is done, and what you can do with it. Also, we're going to talk about some of the components, some of the specific tasks that we do in the boot camp. We go over the specific, training and lectures and classes that we have in the boot camp, as well as like the follow-up meetings, and we talk about each, one of these components in more detail. And more importantly, I think more important than anything, as you see the heroes that are in this like panel, Mike Mattis and Mike Shoding, and we'll have others in the panel, that we want to get these people to explain how they added data science into their clinical and biomedical research, and listen to some success stories. These are the people who are, clinicians and biomedical researchers, but as they will describe through the workshop today and through the boot camp in summer, they have added significant, really significant components of data science to their all the proposals, all the publications, and all the research plans. Those are the success stories that would tell us what to expect and how we can actually, basically use data science for our research more effectively. So these are the people that we will hear from them today, and some of them during the boot camp, and that would be a very exciting, I think that's the most important part of this this training program, to see how people actually do this in real world. So I'm gonna introduce the speakers. I'm gonna skip myself because Jing gave a very detailed and kind introduction. I'm gonna start talking about Dr. Grajek, Jonathan Grajek. Jonathan, are you there? I don't think so. I don't see him in the panel list. Anyways, Jonathan is a senior scientist in Midas. He's also an assistant research scientist in the Department of Computational Medicine and Bioinformatics. His research focuses on development and application of machine learning and data science techniques in computational applications in computational medicine, as well as development of algebraic cryptographic systems that he also applies to biomedical applications. He has worked for private and public entities and different capacities, and right now he's essentially one of the leading scientists in Midas. So that's Dr. Grajek. We have Dr. Shoding here in the talk. Dr. Shoding is an assistant professor in Division of Pulmonary and Critical Care Medicine and Internal Medicine. Mike's primary research is how best to measure the quality of hospital care, with focus on intended and unintended consequences of current quality measurement programs. He's also interested in the use of high-dimensional data to enhance our ability to measure and improve the care of patients with critical illnesses. He focuses mainly on ARDS and sepsis as the major diseases that he's working on. Methodologically, his work employs the use of both clinical and large-scale administrative databases, multi-level statistical modeling, causal analysis, and simulations. He's been funded extensively by National Science Foundation, National Institute of Health, and other organizations. And Mike will give a talk today about his work and how he uses data science for clinical applications. The next person that is also present now in the panel list is Dr. Michael Mattis. Mike is assistant professor of anesthesiology. His research interest is focusing on improving preoperative care for patients with advanced cardiovascular diseases. He's also working for intraoperative care, also postoperative care, funded by some grants from Department of Defense. I'm sure some of you are familiar with MPOG, Multi-Center Preoperative Outcome Group, which is an international consortium of preoperative databases, and serves as the coordinating center, and Mike plays a lead role in integration of MPOC data with data from national cardiac and thoracic surgery registries. He is also interested in leveraging novel data science methods to understand patterns with highly granular intraoperative physiologic data, mostly focusing with physiologic signals and waveform data, studying hemodynamic responses to surgical and other types of interventions and in detection of cardiovascular diseases such as heart failure. So Mike Mattis also gives a talk today, and we're very happy to have him today. Next person I want to introduce today is Dr. Matthew Davis. Matt is not giving a talk today, but he will be one of the instructors during the boot camp in summer. Matt is an associate professor in Department of Systems, Populations, and Leadership. That's within University of Michigan School of Nursing. Matt is a health service researcher who has additional training in data science. His research focuses on leveraging large sources of data to study important policy relevant issues. He has made several important contributions to a variety of areas, including identification of dietary source of arsenic exposure in the US population, studying national use of health services over time for non-specific back pain, and development of methods to use social media data to measure social support and public opinion. His work on analyzing social data for health monitoring has been cited significantly in the literature. Matt it has been funded extensively by National Institute of Health. For instance, like he's working on investigating health service substitution for non-specific back pain and other research that he's been conducting. And then, so like I said, Matt will not talk today, but he will teach during summer. So is Dr. Nambi Nalasamy. Nambi is an assistant professor in ophthalmology and visual sciences. His research focuses on machine learning and application of machine learning on clinical informatics and clinically relevant computer vision challenges, endothelial diseases, and novel surgical techniques for endothelial dysfunction, high-risk corneal transplantation, diagnosis, and therapies for ocular surface tumors. Nambi, just like Mike Mattis, who were engineers when they were doing undergrad, so they have extensive and masters, so they have extensive data science background, and they're heavily using techniques such as signal processing, machine learning, and image processing for their research. And last, we saved the best for the last, is Dr. Brahmaji Nalamuto. Brahmaji is giving a talk today. I don't think he's still here, but he's one of the speakers today. Brahmaji is a professor in Division of Cardiovascular Diseases and Department of Internal Medicine, and he's the director of MyChamp, which is like an interdisciplinary center that focuses on using data sciences for health applications. Brahmaji is essentially his research focus is on improving the use and performance of coronary angioplasty and stenting acute myocardial infarction and the care of the patient with cardiac arrest. His work led to long-term collaboration efforts and investigations in various diseases related to cardiovascular health. And he's recently become very interested and very involved in using new analytic tools and methods for measuring quality and cost of cardiovascular services. His research has been funded by multiple grants and from different sources like National Science Foundation, National Institute of Health, and American Heart Association. He has published extensively in journals such as New England Journal of Medicine, JAMA, Annals of Internal Medicine, and so, other places. So with these people who are helping us with this exciting workshop, we want to look at the schedule and see what to expect today. So after this, I will talk a little bit more about the goals and general overview of the training program, and we talk about who can best benefit from that. Then we have a well-deserved break, and after that, Brahmaji will talk about why training in data science would be necessary for the biomedical researchers. And after that, I will talk a little bit about all these buzzwords that we're hearing, and like we don't know how they're different from each other. Data science, machine learning, artificial intelligence, and statistics and everything, they all have very significant overlaps with each other. We want to see how they really different from each other, and what they mean, and how they can be used for clinical applications, for medical applications, for biological applications. And more importantly, we want to see what are the parts that are heavily used and what are the parts that are underused, and people can look into that more closely. Then we have a lunch break. Unfortunately, with the COVID-19 issues, we're not in one place, so everybody gets his own or her own lunch. But then I will talk a little bit about the boot camp and the content of the boot camp, and what we do in the follow-up meetings, like basically phase 2 and phase 3 of this training. After that, so we have some wrap-up ideas and like Q&A, but then James has created a really fantastic virtual networking session for us, which happens within an environment called Remo. And at that point, anybody who's interested, we can go into these rooms in Remo and discuss specific questions and topics. As you see, there's a little bit of change in the timing. We wanted to make the workshop a little bit shorter. So I'm gonna hopefully talk more briefly in the previous part of this, and then we have more time for networking. So with that, I think we are at the point that we can start talking about some specific goals of the workshop. So let me switch to another presentation here, and then we're ready to talk about that. All right, so first thing we need to ask ourselves is why data sciences for healthcare, and why data sciences are actually needed for decision making, for clinical or biomedical decision making. So why data science is more important today is because we are in medicine and in biology, in medical sciences, we are creating huge amounts of data. I'm gonna borrow this slide, part of this slide from a colleague of ours, Dr. Kevin Ward, who always shows this patient, these little patients in ICU, and ask a very obvious question: how much data are we collecting? Imaging, monitor data, lab results, all of those things. How much data are we collecting for just this little patient? This is actually a study that IBM did, IBM Watson Group did, and they wanted to see how much data is produced in typical clinical practices. I'm sure some of you can guess, like, so the specific question I'm going to ask is how many numbers, how many actual numbers are created every second this patient is in the hospital in an ICU? How many numbers, like, different sources, but like, how many numbers are we talking about? Every second, I ask that in different meetings, and people come up with like, 10 numbers per second, 100 numbers per second, and so on. But in reality, we're talking about over 100,000 data points that are collected every second that this little patient is in the hospital. And these are typical cases in ICU. So we are talking about a huge amount of data, and assuming that, let's say, for this little patient stays in the hospital for 1 week, just think of how much data is created. And every day that the clinician goes and check this little patient, they have to consider a huge amount of data collected between the previous visit and this visit. And no one can expect humans to do have the ability to analyze so many data points, such a big database. It's very difficult, and it has basically human ability to analyze data has certain ceiling, and you cannot go beyond that. And I'm going to add to that it's not just the size of the data. Just think about the fact that this data, each one of them is coming from a different source. Like, we're talking about images, we're talking about signals. And not just that, in each of them that you look at, like, let's say, look at an image, there are so many sophisticated patterns that may easily go unnoticed if human users are looking at it. Let me like look at some, scenarios. Look at this videos and images, like this is a coronary angiogram. You look at all the data, every single point, every single pixel in this image has certain, information and patterns that are very difficult to be captured by human eyes. And then you have the monitors creating all these waveform data like electrocardiogram, PPG, and other sources of data. And again, these data has a whole lot of, sophisticated patterns that, human eyes is simply incapable of extracting and noticing. And then we have EHR data and demographics, and they have a whole lot of data, in there that is talking about all the comorbidities, medications, and everything, history of the patient. And not just that, recently, we have more and more cellular, molecular, and omics types of data, and these are coming at different levels of, biological stories of what is happening behind the disease and what to consider. And again, it is very unrealistic to expect that a human can analyze all of these data, not just the size, complexity and diversity of the data, and come up with an informed decision. More and more, the human becomes a decision maker sitting on top of a whole lot of algorithms that are in an automated fashion. They're analyzing the data and presenting just the extracts of and like, summary of what the data is telling to the patient, to the clinician, and clinician is the person who's looking at these recommendations and make the final decision. But before the clinician can make a decision, just see how many algorithms have to be, in action in order to create something that is presentable to human eye for predictions or decision making. So what is data science? I'm going to start with the definition, the official definition that National Institute of Health has created. So I'm going to read it for you. The interdisciplinary field of inquiry in which quantitative and analytical approaches, processes, and systems are developed and used to extract knowledge and insight from increasingly large and or complex sets of data, right? This is like, a very sort of vanilla definition of data science, but at the same time, it expresses what is happening. What I'm going to show you is a diagram very close to, very similar to the diagram that Jing showed us at the beginning of this workshop. And I'm going to put some more detail and put it in the context of this particular workshop. So I'm going to define data science as the intersection between three different fields. One is math and science. Obviously, without math and science, there is no algorithm. There is no, there is no theoretical foundation for anything. But if you have math, if you have a bunch of equations, that doesn't mean that you have, a solution. In order for any mathematics to become useful in real application, you have to put them in form of algorithms. And this is the task of, computer scientists who are starting from a bunch of mathematics, and they create an algorithm, a program, a code that would, conduct a task, perform a task. And of course, it would be useless if you have all these math and algorithms, but you don't know why you're developing that, and there's no goal for that. So that's why you need to have discipline. In this case, we're talking about biomedical sciences. So these biomedical scientists should sit and define the problem, then design a math and write algorithms in order to solve it. And there it is. This is data science, which is at the core of, the intersection of all of these things. And there are entities that are in here, part of the data science and around data science, that are very important. We hear a whole lot about machine learning. We talk about traditional research that is happening mostly with statistical methods. And we have, regular informatics that are more like, coding, but not much math involved in it. So I want to tell you that the borders between these things are very, very unclear. We will make an attempt in one of the, next talks. We try to clarify that a little bit and have more, sort of distinguish these from each other a little bit more. But what I want to say that in general, the areas that we care about a lot, there are three major components. One is a statistical learning method, a statistical method, and this training is not for statistics. We are not doing the statistics in here. We go machine learning, we go data science beyond the statistics. Mostly we will focus on artificial intelligence and the major component of artificial intelligence, which is machine learning. And we will talk about that later on. I will get back to this. And I know that at this moment, I'm just telling you, oh, it's all fuzzy, like everything is, overlapping with the other one. I will try to, at least in my view, to give a little bit of more, sort of hierarchical structure to all these buzzwords, so that we know when we're talking about one topic versus another one, how they relate to each other. But all we need to know at this moment, before we get to that, during the workshop, is to know that artificial intelligence is the focus of this training that we provide. And in particular, a major component of artificial intelligence, which is machine learning, would be at the core of everything that we cover in this training. Now, what are the main, with this introduction, you're asking yourself, what are the major trainings, major skills I need to have in order to do data science? Obviously, you need to have some knowledge of math. And what specific areas of math you need in order to be an effective and efficient data scientist? Obviously, you need to know calculus. And for this training, for this workshop, we are assuming that you remember something from the calculus. You don't have to remember everything, but calculus is a must. Then linear algebra, which is extremely important as you get more and more advanced methodologies in data science, you need to know more and more linear algebra. We're not assuming that anybody knows linear algebra for this training. You don't need to have any background in it. Same thing with optimization, which is sort of combination of the two. And again, optimization, in order to do really like focused data science, you need to understand the topics in optimization, but not for this training program. We will not talk about that. You don't need that. Some knowledge of statistics and probability. Good thing is that when I look at the background of people who registered for this training, regardless of the specific discipline that you guys are coming from, you have some knowledge of statistics. And more importantly, we are not designing this training to teach statistics. There are many other types of trainings out there that in training programs across the campus that focus on statistics, and I will get back to that. I will mention some of these resources. But having some knowledge of statistics is necessary for data science. And you need to have some programming skills. Again, we are not assuming that when you get into this, you have programming skills, but we will help you develop some programming skills in Python in order to be more hands-on kind of data scientist as you start working in your own application. But the most important thing, the most important skill is have the ability to question anything that is coming from any computational model. You will see a rather I wouldn't use the word pessimistic, but I would say a very careful approach that I have towards data science, because data science is like a double-edged sword. It can hurt you more than it can help you. If you don't use it properly, if you just run the data, give TensorFlow, MATLAB, whatever, Python, throw some data in it and get something out of that, and you think, oh, I got some good accuracy, whatever. If you jump at the conclusion that what you have is a true model that can truly represent the data and the system that you're modeling, you can hurt yourself a lot. And I would say I am concerned about a whole lot of research out there, maybe some of my research that may not be truly reproducible. It's not about the fact that, we're not talking about plagiarism or anything or falsifying results. Absolutely not. I'm talking about jumping into conclusion too fast and not being truly aware of the complexity of the model that people are using. And as a result, ending up with something that is not repeatable, not reliable. That is the major concern I have. And I think, hopefully, by the end of this training, you will be very knowledgeable, much more knowledgeable in data science, but a lot more careful in using that you question anything that is coming from any of the models and try to be more critical of what sort of data science gives you versus number crunching and getting some nice results. So who can not benefit from this training is a person if you have had a training, a class or something taken in artificial intelligence or machine learning. All you do is you get bored because we're not getting into something complicated, sophisticated related to any of these fields. So I give you the warning ahead of time. If you have done courses in machine learning or in artificial intelligence, it may not be a good idea to waste your time with this one. But anyways, if you have had training, you may want to go to a more advanced one. We're not going into details of any of these methodologies either. We have an intuitive approach towards that. The other thing, if you're not planning to truly use a lot of quantitative approaches for your work, and you wish to stick to standard statistical methods, and in many research that I've seen people doing across the campus, maybe these statistical methods will be just fine. You don't need to get into machine learning and artificial intelligence. If you feel that the statistical techniques are working for you, I would say stick to them and use them. They might be simpler than advanced data science, machine learning methods, but at the same time, because of that, they're probably more reliable, they're probably more robust against the errors that people can make and have results that are not representing the data. So I would say if you don't feel that you really need data science in your research, there is no need to take this training course, because if you're happy with the statistics, the standard statistical method, I would highly recommend that you stick to them. But who may best benefit from the training? These are the people who would like to have an overall understanding of artificial intelligence and machine learning. You understand, you remember some of the calc, and you want to see what people can really do in practical applications using machine learning and artificial intelligence, then that is like something that we can do with that. Our approach to all these trainings would be intuitive. We will have equations, but we'll try not to have too many equations. And more importantly, for any equation that we put there, we try to have some level of interpretation. We would love to have some intuitive understanding what this equation says, as opposed to like the square root of something divided by ln of something else. We want to have to look at not too many equations, but for each equation have some interpretation why we're doing this equation. Oops. Okay. Then another group of people, another benefit of this training would be the ability to effectively or more effectively communicate with data scientists and understand the languages. If you are in any kind of research these days, not just in biomedical research, at one point or another, the data that you produce has to be interpreted by data scientists, by computer scientists, by mathematicians. If you just give the data to them to interpret for you, and you don't know how they interpret that, you are susceptible to all the issues that I mentioned at the beginning. You don't know the capabilities of what they can do, and at the same time, you don't know the problems and false results that can come out of these models. So if you want to understand their language and at the same time have a general understanding of what they're doing, that would be a good way of approaching this problem. Another thing, if you are a junior faculty and you're planning to have your career, as I mentioned a little bit at the beginning of this, if you want to add data sciences to your research as a competitive edge that would distinguish you from others who are doing purely biomedical or clinical research, this would be a good training for you, because it shows you through examples and through through different scenarios how you can get this data, how I can get this training in data science to make your research and your career path distinguish from others. And I think this is one thing that we learned from people like Mike Mattis, Mike Shoding, Nambi Nalasamy, and others who give talks during this workshop and in summer camp that would explain to us how these people made themselves distinguished by having a significant knowledge and expertise in data sciences. So what we cannot expect from this training, that's more important in my opinion, is what one can expect, what can expect from that is to realize what you need to do in machine learning and when to avoid it. I'm gonna quote myself in the next sentence that I'm showing you. I'm gonna quote a sentence that I give, like a phrase that I give to any class that I teach in machine learning and signal processing and whatever. At the beginning of the class, session 1 of the class, all the way through the training, that if you are a knowledgeable user of machine learning, you don't use it a lot. It's not that you jump into machine learning for any application. And once you decide to use it, your hands are shaking because you know the risk that you're taking. It's the double-edged sword that I was talking about. You learn how to be careful not to use machine learning and artificial intelligence when you're not supposed to use it, right? And when you're using that, you will be very, very careful. You will learn how to avoid the issues that can come from that. And communicate again more effectively with data scientists and have and in particular, if you're working in an environment that you will have to work with the students and trainees in the future and or currently working with them, it would be, you can be a far more effective advisor if you understand what these computational scientists working for you as a student think and how they function. You need to, you learn the language of these people, you can be better supervisor, better advisor for them. And write more competitive proposals and better papers with components of data science in it. Again, when we listen to Mike Mattis and Mike Shoding, these people can tell us, how they came up, for example, for the K grants and other grants like R01 grants that they wrote, and how they sort of integrated their biomedical and clinical ideas with data sciences to have a more impressive and more competitive grant proposals. It is not a grant proposal training, but as you will see when we talk about the bootcamp, we have components of that that will tell you specifically how to inject data science into your clinical or biomedical proposals. So you get some training examples to use machine learning. It's not that you will be very advanced programmer, but you will get some training. Now, what you should not expect from this training. One, statistical and training methods. We are not teaching statistics. There are other resources available for that. We are sometimes using statistics, but not sophisticated statistics. To understand some general ideas without, you don't get any details of any mathematical techniques. It's just make it clear. You don't get a lot of details on the math side of that. If you want to have more details on the math, you have to take a follow-up course after that, in multiple departments offer that, computer science department, computational medicine, bioinformatics offer them. You need to take courses on those disciplines and get more advanced classes. And you will have, you don't expect to be a completely independent researcher in the, when it comes to the ideas of machine learning. In other words, you still need to work with data scientists in order to make your proposals, your papers, or whatever truly data science oriented. I mean, I don't want to overpromise what you get in this 1 week bootcamp. You don't expect that after 1 week, you can lead all the components of data science components of your research or your grant, or you write it completely independently by yourself. This training program is designed to give you the ability to communicate effectively with data sciences and understand, you express your needs to them more clearly and understand their solutions when they explain it to you. It's not that you suddenly can design like sophisticated mathematical techniques in data sciences. That's not the purpose of this bootcamp. Again, that's a very novel and good idea. You just, in order to do that, you need to do follow-up courses after this. This training will prepare you to take the next steps, but it's not the point that you gain all those skills. And you cannot write advanced code. Like we teach you some Python, maybe even a little bit of MATLAB, but it doesn't mean that you will write sophisticated codes by yourself. You still need the students to help you, data scientists to help you, but you learn at least to look at the code and have an understanding of what is happening in it. So again, you should not expect to have more details of math. And let's go to the next component, which is data science for healthcare. Let's for a moment, let's say this is the end of the end of your training, right? And you have learned data sciences, and now you want to see what are the opportunities, what are the challenges, what are the things that you should avoid, what are the things that you can do. And assuming that you have all the skills, I think it's important even now for you to know what you can do and what you should avoid. So we're gonna see, once you have the training, what are the opportunities ahead of you. I'm gonna show you a tree that I created for a different talk, for a different training, but I think it's important for all of us to see it. When you see the tree, it's a large tree, and it can be a scary looking, structure, but we're not going to cover all of that. We're not going to talk about all opportunities or all challenges in this tree, but I just want to go over some of these opportunities to see, if you take this training, what capabilities you have and what are the risks involved in it. Okay, so this is the tree that I wanted to show you. It's talking about opportunities and challenges of using data science in healthcare. And as you can see, I have 3 categories in here. Category 1 is technical, like it's related to data and algorithms. And we will try to focus on that, talk about, once you learn data science, machine learning, those kind of stuff, what are the opportunities, what are the challenges? Then we have 2 other categories. One of them is health and clinical challenges and opportunities. Another one is cultural, socioeconomic, and policy-related challenges. These 2 branches that unfortunately we don't have, for 2 reasons, we're not going to talk about it. First, we don't have time. Secondly, I'm not the person to talk about them, because this is not my expertise. You have to find someone who knows what he's talking about when you get to these things. But I want to say these are as important and as impactful as the technical challenges and technical opportunities. If you don't have, like for instance, let's say we're talking about the legal issues involved in using machine learning or data science for healthcare. So a patient comes, an algorithm analyzes the data, says we triage this person is not going to make it, right? And if the clinician relies on that, assessment or prediction that the algorithm makes, and something goes wrong, right? Or they make a treatment, algorithm suggests a certain treatment, certain medication or surgery, and something goes wrong. Now, who's the liable party here? Are we talking about the clinician, the hospital that acquired that machine learning algorithm, or the company that created that machine learning algorithm? I have to tell you that there are so many ambiguities and challenges in that side, and so many opportunities to have the very interesting and impactful conversation with attorneys and others, healthcare providers and insurance companies and everyone involved in this ecosystem. But what I want you to know, that there are so many consequences on that side. And I would say the reason that artificial intelligence and data sciences haven't been, there's so many papers, so many grants, so many research out there, but the reason that they haven't been entirely, they haven't been very successful in making solutions and systems that are used in clinical practice in today's medicine. Most of the challenges is over here. The ethical, legal, and cultural issues involved in it, right? So that every machine learning algorithm, let's talk about cultural and policy related issues like the equity issues and all of that. We know that there are some biases in the data that we're analyzing, and regardless of what you do with the algorithm, these biases will be represented, will be present in the machine learning algorithm. And now, how do you try to eliminate these biases, or at least reduce the impact of the biases into the practice that is using these machine learning algorithms as the solution? So that is like a very important sort of aspect of using machine learning or artificial intelligence in any field, in particular for medicine, because you are playing with the lives of people based on an algorithm that may have a lot of biases in it. What I want you to realize is that these two branches that we don't talk to them in detail, we don't just talk briefly about it. They're as important as the branch that we're focusing on, which is the technical challenges, okay? So technical challenges, some of them are related to the data, some of them are related to the algorithm, and I will go through some of them in the following slides, and I will try to make a case that these are important issues, challenges, and opportunities that people have to be aware of and pay attention to. If you do this training, when you do this training, when you're done with this training, first thing that you need to think about is these challenges. And when you're using like these mathematical methods, you have to keep an eye on the issues that can come with them. So let's talk about the first challenge and opportunity, which is related to the data. Keep in mind that the data that we are using in health are coming from very different fields. We have, different modalities for the imaging, different modalities for the monitors, different sensors that are wearable devices that are becoming a lot more, popular these days. We have, different types of omics data that are becoming available, like the different assays, molecular assays and cellular assays that are becoming available for decision making. We have all kinds of data. And when you have all kinds of data like that, your machine learning algorithm is susceptible to so many issues. One of them is being noise, data being noisy. Like, it's if you look at any images in biomedical applications, there is a significant amount of noise. Even MRI, which is like, the gold standard in many cases, it has significant amount of noise and artifact that can interfere with the true analysis of the data. Not just that, labels are uncertain. We have, Mike Shoding will talk about this in more details in his presentation, but a major issue in training machine learning algorithms is how to annotate the data properly. Because, for instance, you get a patient to the hospital and you show the data of this patient to 10 different clinicians, and they may end up with totally different or not the same sort of diagnosis about the patient. So how do you train a machine learning to predict the same thing, to sort of emulate the decision-making of a human, if humans don't agree about the label of this data, right? Some may say that this person has, this disease. Some people will say a different disease, and some people will say, oh, the person is doing fine. And we have shown these cases in our studies a lot in the past. Like Mike Shoding will talk about the study that he did with ARDS and, showed the data to multiple clinicians, asked them to say whether this is ARDS or not. At different times, like they keep looking at the patients, and you'll be surprised, you'll be amazed to see how much, inconsistencies may exist among, and lack of agreement may exist among clinicians. And now I want to create a training data and feed it to the data science method, let's say machine learning method, to model the way human thinks and make a prediction about, the health or disease or whatever. How do I label it? Am I looking at clinician A or clinician B? How do I average them? And eventually, when I want to, let's say now with some magic, I trained my machine learning algorithm, and now I want to put it in action and use it in a hospital. It makes a decision, and then again, clinician A looks at it and say, that's not right. Clinician B looks at it and say, that's right, I like it. And everybody can have their own opinion about what the trained neural network or machine learning method is doing. So the labels being uncertain is a big, huge challenge for any kind of data science that we're talking about. Now, again, I keep talking about the challenges, and I will talk about opportunities as well. There are, again, the solution to these problems exists within the world of mathematics. And again, Mike Shoding will talk about that potentially, or just, mention that briefly, that with mathematics, you can do the best given this like messy situation. And some mathematical technique would allow you to, with some really good, levels of success, deal with this uncertainty over the data or the labels. So this is a challenge and an opportunity. So when we talk about data science, the vanilla method data science that we cover in this class, we will also talk about, briefly talk about what are the more advanced methodologies that may address that. We don't cover them, but we talk about, the existence of some methodologies that can handle those issues. Another challenge is that data is coming from different places and they have different modalities of saving the data. They have different types of databases and the connectivity between them doesn't exist. More importantly, a patient, and I can tell you this is like a major issue in some of the studies that I've seen. A patient goes to different hospitals and healthcare systems for the same disease over time. First, they go to the local clinic and then they go to the local hospital and they may go to like a more equipped, more advanced hospital. And the connectivity of the data through this process is not there. Like, we wish to think, we would love to see that this connectivity is there, but it's not there. Some of the data gets sort of lost through this process. And, let's say like the patient goes for the regular visits to the clinician after a surgery, and this data is not necessarily shared with the clinician who performed the surgery. So if there are long-term consequences or like, issues coming from the surgery, it's not well communicated. And if I don't have a database that has all of these in it, data science methods cannot do magic, right? I will misinterpret the data, because if the patient after the surgery every day went to the local, the family physician for this and was complaining about this and this and this and that related to surgery, and I don't have it in the database that came from the hospital that showed surgery was successful, how do I train a machine learning to handle that, right? So I wanted to see the challenge in here that, if you just get the data and without thinking, throw it into a machine learning algorithm, all you get out is garbage, basically. So, and then there's an issue of privacy and security over the data. Like, if you have personal health information or identifiers in the data, you don't know how to, analyze this without, compromising the security of the data, the privacy of the person. And it's also a big challenge has been a big challenge for many years. If you have all detailed data about the person, this database becomes too sensitive in terms of patient privacy, and you don't find many databases, large databases like that. Again, I'm talking about the challenges, and I'm telling you that there are solutions that are coming from data science as well. These are challenges for data science, but the solution also comes from mathematics, from data science. There are solutions to handle these cases, and I would say that these solutions are becoming very effective these days, but I just want you to be aware of, the challenges that the vanilla standard methodologies that we talk about may have in dealing with them. So let's talk about the second group of challenges, that these are algorithmic challenges. One is generalization and validation. I can tell you that, like I mentioned, like in a few minutes ago, that I'm really concerned that many of the research, many of the solutions that are created using data sciences are not repeatable. And the reason that that this problem exists is because they have not truly validated the generalization capability of the method. If all the data that I'm using are coming from a sort of a local hospital, every algorithm that I'm getting would be customized, specialized towards that local hospital. I cannot use it for another hospital because, like, geographical and all the socioeconomic issues that are defining the patients going to this hospital will not be generalizable, right? The other thing is that some of the algorithms, like machine learning algorithms that they're using, such as deep learning, which is very popular these days, they need truly large databases. If you have 50 million parameters in your machine learning, in your deep learning method, and you're training that with the data coming from 50 patients, you're not getting anything. You're just overfitting the data. But unfortunately, these are the challenges that, mathematically, there are solutions for them. There are alternative solutions like methodologies that should be used if you have like 50 patients. But you will see that there's a whole lot of publications, grants, and whatever coming out, and they're using wrong type of machine learning, wrong type of data science for the problem that they're dealing with. There is nothing wrong with these methodologies. Methodologies are defined to handle the problem that are designed for properly. But if you use them and if you take them and use them in the wrong place, they're not going to solve anything, right? It's a wrong key for the door, right? You have to get the key that matches the door. So like I said, the diversity of the data and training and testing is a major challenge and major issue with the existing systems. The other thing is, most of the data that we get has some structure, has some temporal, at least temporal structure in them. Like the patient goes to hospital day 1, day 5, day 6, or if the patient is in the ICU, we have, every second we have the data. And which means that you have to use this temporal pattern in the data in order to have a more meaningful data science solution for the problem, to predict whether the person will do better or worse in the future. But in reality, you will see that some of these techniques are not designed to deal with the temporal nature of the data. And if you get, again, the wrong key, you cannot open the door, because this structure, for example, most importantly, the temporal structure is extremely important for getting the right pattern, right? When I'm talking about the structure, people always think about the structure in time. Let's think about structure in other dimensions. So let's say you have an image, right? Image is a two-dimensional entity. You have like rows and columns, right? If I have an algorithm that can deal with an image, you feed an image as an input to the algorithm. The algorithm is designed to deal with two-dimensional data. The algorithm will be able to analyze it properly. But what if the algorithm that I'm using is just getting a vector? It gets like a sequence of data, like a line of data, a row of data. What people do, they get the image and vectorize it. They get like, first row, concatenate the second row to the end of that, and to the end of that, the third row, and so on and so forth. So they make like a two-dimensional entity, a very long one-dimensional entity, in order to feed it to that data science that gets one-dimensional entity, right? One-dimensional input. Then you're compromising the structure. How do you expect this machine learning to be able to interpret the data as an image? Let me give you an example. What is the ultimate machine learning, like artificial intelligence? Is the human intelligence, right? So if you show me an image of a tree, I will immediately tell you that's a tree. But what if you do the same thing that you did with, like in case of artificial intelligence, just get every row of this image concatenated to each other and show me a very long, just one-dimensional row of gray level or whatever, RGB. Can I look at it and tell you if it's a tree or not? Absolutely not. Like humans, who are the goal of artificial intelligence, when you compromise the structure, when you destroy the 2D structure, make it one-dimensional, they're not capable of telling what you're dealing with. So keeping the structure is very important, and unfortunately, this is compromised in so many applications. The other thing is the transparency and communication of the results. Majority of the methods that we use in machine learning, they're black boxes. You don't know what is happening inside them. Like all these deep learning neural networks, they create a box that makes you prediction. You give them the input, they give you prediction or recommendation. But you cannot ask them why you made that recommendation? What is the pattern that you saw in the data? Those are not, in some application, you don't care about that, right? The person, like, the paramedics in the front row of the battlefield, they have to make a quick decision about whether to give this like treatment to the patient or not. They don't care really much about why they have to do that, but they have just the time and resources to make a decision based on recommendation. They may not ask why, but if you are in level 1 trauma, hospital, then that is like, you want to know why you're making that prediction, why you're making that decision. So transparency is important. Because of that, some machine learning methods that have transparencies match those type of applications, right? And we talk about that. And even today, I will get back to this in more detail. And choosing the right clinical outcome. I would say a good chunk of what you see in the literature, they have fantastic data science methodologies, but for predicting the wrong thing. Like as an exaggeration, what would be a very, very, very accurate machine learning that looks at, and this is the machine, what is inside the machine learning. If there is no pulse, if the person is not breathing, if it's like, if you have this and this and that, the person is dead, right? It's a very accurate machine learning algorithm, but it's predicting something that humans can see when they don't need machine learning to tell them. So using, or sometimes they make like predictions or recommendations that are not, you cannot use them. Like if you say like, leave this patient die, right? The person is alive, but don't do anything about it. Just leave it. That is ethically an issue that you don't want to, you don't want to deal with. If the machine learning has to make a prediction or set of predictions that are actually actionable, right? So last thing I want to say is that in practical thing, what are the, the long-term, near-term and long-term solutions that these machine learning methods or data science method can create? In near term, and this is like my personal opinion, I discussed that with many people, got the feedback based on that, but still I will consider that my personal opinion. In near term, like when you're creating these algorithms, best way of using that is for like auditing and assessment, because you're not everything is like it's offline, and it's you're not making a decision about life and death of your patient who are in the hospital, right? You're talking about inefficiency, waste, abuse, insurance thing. You can use these methodologies, assuming that you deal with the biases that is in the machine learning. It will tell you a whole lot about the capabilities of these machine learning, this data science methods, and you can train the method with this and prepare for the next phases. Then you can use them for remote monitoring. If the patient is in the hospital, it's very difficult to go to a clinician that has like 20-something years of experience to say, oh, don't do that, machine learning is telling you to do this, right? But you can, but for the cases that there is no clinician in the room, the person is like, walking outside or sitting at home watching TV, there is no clinician, and you're doing remote monitoring of the patient. Like there's some wearable devices that monitor the physiology. In those cases, going with what machine learning predicts might be easier, because it's easier to convince people that's the only thing you can do, right? But the good thing about using these applications in near term, more and more of these applications, is that it will show the capabilities of machine learning. You correct for the errors that machine learning can create. You deal with the biases. You sort of improve significantly what data science can do for biomedical sciences. And then you're ready to go for the more long-term applications of these. I'm not saying that these long-terms haven't started. Some of these are being done. But the reason you don't see a lot of solutions that are truly data science solutions used in clinical practice is because I think there's still like, we have a few years ahead of us before we see them implemented in real world. Then early clinical diagnosis. Many of these patterns that you see in the complex type of data may not be visible to the human eyes early throughout the process. Like they don't see, humans are fantastic in seeing some patterns, but this pattern has to be significant, visible. Algorithms, on the other hand, can see very subtle changes that would precede the actual event. And I think for early detection, again, it's easier to convince clinicians in the future, or the hospitals and insurance companies, or legal sort of authorities, that for early detection, machine learning is the only solution or the best solution. We have to go with it. And finally, we can do it for resource allocation and decision-making scenarios that are very important, like the real applications of ultimate goal of this. So this is what I had for this one. Let me stop sharing. This is what I wanted to talk about, the goals, and give some sort of understanding of what to expect and what you learn at the end of this, how you can use it, and how careful you have to be if you want to use them in real world, right? We have 3 minutes before the break. So since we have plenty of time for Q&A in the afternoon, we may want to skip the Q&A and for this talk, and we take a break for 15 minutes. After that, Dr. Nalamuto will be here to give his talk, and then we continue with the rest of the workshop. James, we just mute ourselves and come back in 15 minutes, right?
Yep, that's correct.
All right. Okay. Thank you, guys. See you in a little bit.
All right. See you all in a little bit.
So I know I gave a long introduction of Brahmaji at the beginning of the workshop, but just like 2 more sentences, and we let him start. So one thing that most of you, I'm looking at the list of people participating, most of you are familiar with the extent of mentoring that Brahmaji had for many of us in this room, and helped us with the clinical aspect of how data science can be used in real world, and he has impacted the career of many people in this room. And I think that's the reason I thought that Brahmaji would be the ideal person to show us what is happening on the clinical side and guide us through the process. So thank you, Brahmaji. I know your schedule is very busy, and despite all of the other obligations that you had, you accepted to give a talk. Thank you very much, and the Zoom is yours.
Thanks, Keyvan. Can you hear me?
Yes, loud and clear.
Great. Well, I'm going to try to share my screen here. Every time I go into presentation mode, it doesn't seem to just blacks out. How is that?
We see
Right now,
all your
black.
We see all your
Great.
slides. So if now it's good. We see the presentation mode. We see like the next slide. It's good enough, I guess.
Good enough. Okay.
Yeah.
All right. Okay. Okay. Well, so it's really it's a great pleasure to be here and to talk with this group. I think it's wonderful that the Keyvan has put this type of workshop and boot camp together. I think this is really meeting a great need in our community. I've met Keyvan like well over 5 years ago now, and I can tell you that having kind of gone through this journey a little bit on my own, kind of being a physician scientist who used what I would say more traditional methods for a number of years, and got excited, probably reading too many Wired magazines or listening to podcasts about this whole thing around data science and machine learning and artificial intelligence and how this could potentially be applied to my own work. I got very excited about it, and I've really come to believe that there's this really delicate balance between hype and hope with these tools, and this will be a very low intensity talk. It's more a bit of storytelling around my own experiences and maybe some lessons learned is what I'll finish with, around how, many of you are already here and interested in this space, might be able to navigate it and kind of learn from some of the things that I've been through. So, the title that Kayvon gave is "Why is Training in Data Science Necessary for Physician Scientists in All Fields?" And, I think I'm going to just assume that since you are here and you're dedicating this time to it, that you already know why it's necessary. And I'm going to focus a little bit more in how is training in data science possible for physician scientists in all fields, and in particular, focus on how you can do this perhaps more successfully than many of us who've kind of gone before a lot of you. So this is my disclosure slide. All right, so I'm going to start with a story or a joke I oftentimes like to tell, which is a computer scientist, a statistician, and a cardiologist walk into a bar, and what happens next? And I think for most of you, absolutely nothing happens. And the reason behind this is that there are so many things that are in the way, challenges, barriers, whatever you want to call them, that really prevent, true kind of multidisciplinary work. And this story is actually based on how I met Kayvon. I met him actually at a bar that was put on by MCirc. It was a get together, and we had to do these like rapid, kind of rapid dating sequences where you had to like pick up and move every 15 minutes or so and meet with someone new and talk about what you were interested in. And actually, during this conversation is when I started to understand that Kayvon was interested in angiograms. The angiograms he was interested in are angiograms around kind of the blood vasculature in the tongue, and he had done some work in that space. And I'm an interventional cardiologist, and my clinical work is based on actually, angiograms. It's based on obtaining angiograms and then making decisions around them, and then actually clinically intervening if necessary. And so, this kind of chance meeting led to a lot of collaborations, and actually, several years later, we still work very closely together on different projects. And one of the biggest joys has been kind of co-mentoring, trainees in his lab as they start to kind of develop their own work and agenda. So I'm going to spend some time today just talking at a very high level about things that physician scientists oftentimes wonder about, which is, what is data science? What does it actually mean? What is the challenge for physician scientists in this space of data science? And then how can physician scientists maximize their impact within the field? And then finally, I'm just going to end with a few lessons learned. So what is data science? And, I love this piece by David Donoho, and it's, the link to it is at the bottom here. And this is actually a paper he put together. It was actually part of a presentation he did as John Tukey is a very famous computer scientist, part of a lectureship in his name. And what's really interesting is this a piece in paper was asking some of the fundamental questions about the origins of the term and what its role is. And I wanted to kind of highlight one particular aspect. He actually gave this talk about data science right actually on the same day as when the Midas Initiative, which is sponsoring obviously this event, was announced here at the University of Michigan. So about 5 years ago. And he notes this actually in his remarks, and he talks about how this idea of data science was really growing in communities all across the country. For us in the healthcare area, this has probably hit us a little bit later than it has many other industries, but certainly an important area and part of like kind of data science initiatives. So, he talks about data science was announced by Martha Pollack when she was here as becoming the fourth approach to scientific discovery, in addition to experimentation, modeling, and computation. So a very big claim. And then also went on to describe at least what Midas had originally described as the data science initiative and its role. And they talked about it coupling scientific discovery and practice, involving the collection, management, processing, analysis, visualization, and interpretation of vast amounts of heterogeneous data associated with a diverse array of scientific, translational, and interdisciplinary applications. And you can see that this definition is both broad, um, but also very difficult to understand how it distinguishes itself from other core areas that we think about. And one of the big debates has always been like, how is this any different than statistics, for example? I mean, statistics has analyzed data in vast amounts of heterogeneous data in a number of ways for several years. And this confusion between what is data science, what is computer science, what is um, what are their specific applications, where do they differ, how does it all interact, is something that as a physician scientist looking from the outside has always been a bit difficult for me. And I think it's particularly challenging because there's this buzzword and hype application to data science that I think we see through a lot of our different communities. So, this is something that I still struggle with at times. I think the best way that I thought about it is this Venn diagram that you'll oftentimes find folks talking through, that it really is this intersection between lots of core disciplines that we think about. And really it's about this kind of intersection between what folks will talk as computer science, more the math and statistics disciplines, and then obviously the domains, the business knowledge. In our case it would be the life sciences, or the healthcare sciences, or medicine itself. And it's at this intersection, so it's a very applied area, and it tries to take into account all of these things. And this debate goes on and on about it, but I think for me, it's been a way of actually visualizing what this really means. So with that in mind, the question really becomes, what challenges may exist for physician scientists as they start to work through this? Well, I think that there are a handful, and there are three that I wanted to kind of emphasize here. The first challenge, which I've kind of found in my own career, is that we're behind. Many of us, even though we seek to really understand and apply data science in a lot of our work, have to realize that we are far behind many others who have been in this space for a while. And this is a really interesting report that came out of Stanford just this year, talking about the rise of the data-driven physician. And they did a survey of physicians as well as medical students. And one of the interesting things that they have found is that there's this real hunger for data science within kind of the medical professionals. So in this one, you can see on the figure to the right, a couple of the key diagrams that I thought were quite interesting is where nearly half of all physicians and 3/4 of medical students said that they are currently seeking out additional training or classes to better prepare themselves for innovations in healthcare. And then when it comes to like what types of classes they're looking at, you can see the range of different courses there in the bottom figure, right? So almost half are looking for advanced statistics and data science classes. Um, Many of them are looking for, even a quarter of them are looking for coding and programming classes. And then some, about a tenth or so, are looking for applications that are directly related to artificial intelligence. So it just speaks to like how this is, a real need, because I think many of us feel like we just have not had this as a core discipline or coursework within our training. This is probably the reason why many of you are actually, participating in this workshop, um, and then the boot camp as well, is trying to understand how you can take these tools and bring them into your own fields and work. So another challenge that exists is, and this is something that I think many of us live, is that we're very busy, right? I mean, we have numerous competing interests with clinical care and traditional methods, research methods that we're already trying to apply and use. And trying to think about how to bring in an entire field of new tools that data science can often offer into your own work and current thing. It's just almost like so many things that just can't be done. And I think that this is one of the reasons why, and it's a theme that I'll come back to later, multidisciplinary partnerships are so important. In fact, they're like critical to doing this well. And a couple of examples, I think you'll hear from Mike Shoding a little bit later, but I oftentimes like to use the model that we've tried to create within our own center, which is called MyChamp, or the Michigan Integrated Center for Health Analytics and Medical Prediction. You really need models like this to build support and engagement. And these are two teams that I think have been extremely successful. So on the very left are Mike Shoding and Jenna Weens. Mike is a critical care doc, and Jenna is a professor in the College of Engineering, and they have built a successful partnership that really has just blossomed, and a lot of it's based on them collaborating through work that's included funding from Midas, as well as NIH now and NSF. And then to the right, Ji Zhu, who's a professor in statistics, and Akbar Walji, who's a professor in internal medicine and gastroenterology. The same kind of like collaborative work that's led to funding through DoD, NSF, and other sponsors as well. So it's just, again, getting back to this idea of a Venn diagram, what we felt is that, when you think about data science and doing it well, it really is bringing together methodologists, clinical researchers, and I think a gap that oftentimes needs to be filled too is informaticians, people who are used to handling and understanding big data at scale. And it's really at the center of those three areas where I think the best data science actually gets done. All right. And so the final challenge I'm just going to mention this morning for physician scientists with data science is that, I'm going to be very explicit about it. I think we're disincentivized in a lot of ways. And I just want everyone here to kind of go into this with their eyes wide open. When you do use these types of tools and methods, sometimes you run the risk of really going against what's already ingrained in your community, right? Sometimes when you run too far ahead of the pack, that can be risky. We have run into this in our own work when we try to publish it. It can be very difficult to communicate in a very succinct way. It can be very difficult to convince others that, we're just not throwing things into a black box and coming out with some magical answer. So there's a lot of education that needs to be done. And I think you just have to be very mindful of that as a particular risk in terms of how you think about your work. And then I'd say the other thing that is disincentivized is our reward system in medicine is different fundamentally. So one challenge that many of you might have is that, like, as opposed to our collaborators in other areas, like, let's say, the College of Engineering or the School of Public Health or the School of Information, how we actually design our own workflows, our students, our lab environment can be quite different, and that can be a disincentive sometimes for trying to track and use these new methods and tools, just because they can be quite different and not understood by our typical sponsors. Now, this is all changing. I mean, most of the NIH institutes now have put out specific calls for data science and artificial intelligence and machine learning, but I still think that there's a real gap that you just have to appreciate as you move forward. All right. So how can you, with all of these things, really maximize your impact as a physician scientist? And I think one critical way is to realize that the data science is truly a team sport, right? There's individuals, but each individual might have a specific aspect of it, of their work and their talents that needs to be leveraged. And you really need to understand what is your role as a physician scientist in terms of the whole entire data science team. Otherwise, I think you're just going to lead to, frustrations and challenges with how you can work within the system. And so, I just took this from, one website, but many have talked about pipelines for how to do a data science project. And, they all tend to have the same type of groups here. And I felt that this is a really easy model. Kayvon will talk with you a little bit about some of the more technical aspects, and I think you'll get some of that information from some of the boot camps as well when they talk about, really the tools themselves specifically. But when you think about how to get a project through, you really have to define the goal of the project. Then you have to figure out how to get the data, clean the data, enrich it, find insights and visualize, deploy the machine learning methods and tools or data science tools, and then you iterate back and forth and then think about how to implement. And I'm going to focus on 4 areas that I think I've learned over the years are where the physician scientists can be really critical in terms of their role in this process. So the first 2 are defining the goal and getting the data. And what do I mean by that? Well, when I say defining the goal, I think it's so important to clearly articulate the problem you want to solve. I can't say this enough. When I would sit down, I remember working with Jenna Weens on a project. She'll bring out a pad of paper and she'll talk to me about the background of the question and the problem, but she'll always hone in. That first hour we talk about is like, what actually are we trying to solve by doing this data science exercise? And what's really critical about those questions is understanding from your own perspective, what would you actually do if that data science tool gave you better predictions or gave you better inferences? What would that mean? Because sometimes even if you have 100% perfect prediction on a problem, it really couldn't change what you would do anyway from a clinical aspect or even a research aspect. And so really at step 1 should be like, what is the problem that you're trying to solve? I think it's really important to realize that you as the clinical or domain expert can really raise anticipated barriers early to the team, right? You have an intuitive understanding of a lot of this, especially at the beginning, that other team members aren't going to understand. And being careful and descriptive about that is so critical up front. All right. So then the other role that I think you play that's amazing and needs to be really emphasized is getting the data, right? I mean, you understand the data so much better at this point in stage than many times the data scientists. So you want to really be playing a major role in terms of identifying the critical features you should be exploring. You should be thinking about labeling and how that's going to happen with the data, thinking about, limitations of the data around missingness and potential errors, and then obviously privacy concerns, which are really important and sometimes get lost to other members of the team. And I think your role as kind of the domain expert is to always keep that up front and in mind. And then also, I found a lot of my role has been in providing logistical support. Sometimes these data can be hard to get to. And so it's really critical that, you weigh in and make sure that, this is a project that has institutional support, has group support, and you can play an important role in terms of getting those wheels greased. So the back half of it, I think you also play a very important role too, especially around insights and visualization, and then obviously the idea of iterating and implementation. And I'm going to talk a little bit about insights and visualization. I think providing feedback throughout the early process of the results is super important. There's a critical role of identifying the plausibility of the results. If they sound too good or things just don't make intuitive sense, that's really important feedback because so many of these methods need those checks and balances to understand what's going on because of the difficulty in interpretation. I think it's really important also to give feedback early on clinical and mechanistic implications of the results that you're seeing. I found that that's probably one of my biggest roles at the time when we're all looking at results together. And then, you do play a big role in terms of helping teams communicate methods and findings to general audiences. I always, feel like with Kayvon, if I can understand what he's saying, then most of the time your readers and your audiences will understand too. And it's about getting from like the more abstract sense of like some of the analytical tools to actually intuition about what these findings are suggesting. I also think that this is a great time to really think about new directions for discovery and where your team might go next with new questions and problems. And then finally, you really do need to iterate frequently to really implement. I mean, this is where I think we oftentimes drop the ball. We build a new tool, we solve a question with an algorithm, but then the hard part of taking that tool and that discovery and actually implementing it within a health system, many of us just either get fatigued by the idea or challenge of that, and so we feel ourselves limited. One of the common phrases we say in my champ is like, the world is not suffering from a lack of prediction models. What it's suffering from is a lack of useful prediction models that are actually being implemented and changing clinical care. This is a great abstract by Karandeep Singh, who's a member of my champ, and I think he might even be doing some of the courseworks for you guys during your boot camp. But he wrote something about the 7 habits of effective predictive model implementation, and you can see these on the screen. And they are very difficult to implement. But they are also at the end game, why we do this, so we can actually change clinical care. And a lot of it's related to, as he alludes to in the conclusion, these social technical barriers that are just as important as any of the algorithmic challenges that you come across. All right, so I'm going to just end real quick here with some lessons learned, and there are 5 of them that I wanted to share. The first is that the question is king. And what I mean by this is think really hard about what kind of questions you want to answer. I always group things into 2 big buckets, and I think we spend way too much time on the first bucket. The first bucket is, how can we do things that we usually do, but just do them a little bit better, right? And when you think about this, the analogy I give is, there are algorithms that can make your spam filter a little bit better over time. And so we can employ those, and your spam filter gets a little bit better over time, and you have less email spam. But most of us are not here to really use these data science tools to just make things marginally better. The second set of questions is reimagining what you can do with data science in your own field. And that takes a lot of time and effort. And frankly, when you see it, it's brilliant and you can recognize it, but spending time with this is really tricky. I always use the example again of driving a car was reimagined as a prediction problem. And because it was reimagined as a prediction problem, we have these autonomous vehicles. They're imperfect, but boy, when you watch them and see what they can do, that's pretty creative. And I think, many of us go into this with these data science tools, and I think we have to reimagine the types of questions and things that we can kind of come up with. So this is lesson number 1 that I've heard, that I've learned over the years. The second is lesson number 2 is to be deliberate, right? To the left on this image is a Rube Goldberg machine. And I use this as an example because oftentimes what I would do in the beginning was I would read a paper and it sounded really cool. There was some type of algorithm that they would use. And I would go and find Kayvon and I would talk to him about it and ask about the application of it. And he would just look at me and just be like, but for what problem, right? Like, having complexity just for the sake of complexity does you no good. If you can use your old tools to solve a problem, then be deliberate with that and do that. Use these tools deliberately when they serve a purpose and bring value to your question. And this is something that's really important, not to just get caught by the next bright, shiny object. Lesson number 3 is to be realistic. I think I mentioned before, focus on your strengths as a physician scientist. What is it that you bring to the table? Either an understanding of the biology or an understanding of the clinical intuition around what is happening. Those are your strengths, right? We all go through a phase where, you might buy a Python book and try to code for a little bit. And I still do that. probably waste too much of my time trying to pretend like I'm going to be a data scientist in that regard. But over the years, I've realized I need to focus on my strength, which is like helping to frame the question, understanding how prediction can be used to better clinical care. And so that's a really important aspect. Lesson 4 is to embrace discomfort. I think you have to be humble in this field. Um, I've gotten very used to asking what I think are stupid questions. At the very beginning, I realized there was a language barrier. They would use terms and ideas that I just didn't really understand. And I felt this like imposter syndrome of not interrupting. But that's where I think building relationships over time, there's not a stupid question that I can't feel comfortable asking Kayvon, for example. He's heard enough of those from me in the past. And so realizing that, again, you bring a particular strength to the question and how you can bring that value to the team, because there is a lot that each one of you can bring to this entire operation, but realizing, when and how to do that is really critical. And then I'll leave you with the last, which is to be generous. So one of the things that's a challenge, as I mentioned, it's a disincentive, is that our reward system within the medical school and health system is quite different from those that are at the College of Engineering or LS&A. And what I mean by that is our promotions, our ideas of success, how we get grant dollars, how we, generate clinical revenue. Those can be quite different. You know, that can be a problem, but it can also be a strength. When you take this mindset of like abundance, that there's plenty of credit that can go around, it can really transform things. An example would be Kayvon works very closely with a mentee of mine, Hamid Gambari, and they've come up with a very structured way in which, Hamid will lead some of the clinical papers, but then, members of Kayvon's lab lead the more kind of basic algorithmic papers, and we send them to different sets of journals and audiences. And in that way, you can be generous with like success. So everyone wins at the end of the day, and everyone kind of gets credit and is able to work on those aspects of their care, within the project. So I think I probably talked enough. I'm going to end there. And I don't know if there's time for questions or not, but I'm happy to answer any if there are.
I think, first of all, thank you very much, Brahmaji. I mean, you explained things so perfectly that, that's why I wanted people to hear all of this from you, because you explain it so clearly and you touch upon very important, aspect of, using data science in medicine. So yes, we have plenty of time for questions, because the talk that I start after that is not as long. So please, if you have any questions, I think James what do you think we should do? Like people can raise hand and you can activate the mic?
Yeah, if people are wanting to raise their hands, I can definitely unmute them if you'd prefer to ask questions out loud. Otherwise, there's always the Q&A window as well, which I'm happy to help moderate and like read off questions as they come in as well.
But since we have some time, if you have questions, let's raise hand and we'll take the question. Brahmaji will answer your question. Seems that the talk was so clear. People don't have many questions, so in that case, I would like to thank Brahmaji again for the wonderful presentation, and thank you very much for the insight and the guidance on this matter. Appreciate it.
Yeah, no, thank you guys, and enjoy the rest of your day.
All right, thank you. So let me try to go to the next talk. Okay, I think I found that. All right. Okay. Do you see the slides in?
Yes, looks perfect.
All right, good. Excellent. So I thought the next thing that we talk about would be what is data science, what is machine learning, artificial intelligence, statistical methods, and all of those things, and how they relate to each other. What are some important methodologies like that? How they used for medicine and biomedical sciences? What are the ones that are available but they're underused? And we're going to talk about that in more detail. Okay, so you will see a bunch of diagrams. You saw that diagram, like the Venn diagram that Jing, myself, and Brahmaji showed that. I will tell you that there are a lot more Venn diagram coming up, but they're different. Okay, so we'll see how we can communicate these things. So you hear so many buzzwords these days. Buzzwords not in the sense that these like concepts are bad. I'm just saying that first of all, they're not significantly different from each other. Secondly, some of them they're very much hyped. They're not as important as they appear to be. So you hear people talking about data science, which is like the core of what we're talking here. People talk about artificial intelligence. You hear the word machine learning. People talk about data mining, intelligence systems, statistical methods, which are have been around for many centuries. Then you have mechanistic modeling using differential equations. If you know the system, you have the differential equations of the system. You know exactly how the system works. You have computational intelligence. People talk about signal processing, image processing, video processing. People talk about natural language processing. So you hear so many different things. And the question that you're asked, how these things are different from each other. What is the difference between them? So I will have some short and honest answer for you. One, I don't know. Search me. I have no idea. If the more I dig into this and like I look at the historical things involved in development of these things, I realize that there's so much overlap between these things that sometimes it's not justified to give him a different name. Okay, so I don't know, and I think that nobody knows the answer to that. I've been asking this question to so many leaders in the field of data science, and they're all either they openly say they don't know, or the answer that they give don't make a lot of sense to me. And why is it the case? It's mainly because these concepts they're overlapping. Sorry, not over. They're overlapping so much that it's not. There may not be even an answer for that. You cannot even say, in reality, what difference might exist among them, right? They just overlap. So many of them are so similar or subset of each other, whatever. So now you're asking the question, so why do we have these so many overlapping concepts, and why do we have like so many buzzwords around? These are my, again, a bit pessimistic but realistic thinking of my thoughts on why we have that. First, people in academia and us want to get more grants, and we want to publish more. If we always talk about the same thing, how do you justify, how do you explain your next grant? You just have to give it a different name. And I'm calling that X today, but I write a proposal tomorrow talking about Y. And that is the way I get more grants and publish more. The other thing is industry. Some of these are coming actually from industry. And industry, in order to have a better marketing of the product, they have to relabel and repackage everything that existed in the past. Like, I'm sure that you have bought products that they claim to be, so it has a different name, and you claim to be like very different from all those things that you've seen in the past. But when you look at it, it's pretty much like it's an improved version of what you have seen and been using forever. So industry has some, role in creating so many buzzwords. But all of that said, I would say that there are some differences that might make some of these approaches perhaps distinguish from each other, distinguish enough from each other. And like, if people are talking about, they're talking about artificial intelligence and machine learning, there is a relationship between them, which we will discuss. They're not exactly the same. There is a relationship between them. So what I will try to do within the next few minutes is to show you what I feel that this is how everything, plays in the space of, data science and the world, right? Computational sciences. So like I said, this is how I see that. I would argue that many people might agree with me to some level, but I'm completely honest with that, saying some people may completely disagree with me. So here's the thing. We're gonna start and talk about, historical aspect of that a little bit as well. So let's say this is the world of data science, which everything exists in that and some outside of that, right? I would say in 1950s, people started talking about something called artificial intelligence. This like large white thing that you see, the oval that you see in here. Artificial intelligence started with, with people talking about regression trees and rule-based methodologies and things like that back in 1950s. And it became very popular. And then towards 1970s, it lost its sort of appeal to some degree because of the hype. People exaggerated the importance of these things or the capabilities of these things, or at least at the stage of development that we had for artificial intelligence at that time, and it sort of died away. But in early 80s, a part of this artificial intelligence, a subset of artificial intelligence called machine learning algorithms, they became popular again. And the reason that they became popular was that in mid-80s, a subset of machine learning algorithm, subset of machine learning algorithm make it popular. Before I get to that subset, I want to show you that there are entities in this world that we're dealing with that are actually, let me go back, that are actually overlap with data science altogether, but they're not completely considered data sciences. We have mechanistic modeling that has been around forever, right? In chemistry, people use like, differential equations to show the interaction between different agents and things like that. They were doing, and in mechanical modeling of biomedical systems, they were using all these mechanistic model that shows like, Newtonian sort of physics to show the relationship between entities, and later on, even quantum relationship between molecular activities. The difference between mechanistic modeling and data science, first of all, they overlap in terms of technology and methodology that they use. There's significant overlap. But as you see here, there are some part of mechanistic modeling that is different from data science. And those are with the assumption that you know exactly how the system works. You have a set of equations that describe the nature of the system. So you don't even really need to rely too much on the data. You just like say, this is the laws of physics that govern this system like that, and that's it. There's sometimes they have issues with parameter estimation, and for that, they will get into data science, okay? So you see a field that overlaps with data science altogether, but it's slightly different, mechanistic modeling with differential equations. There's another field that you're more familiar with, and that's statistics. Statistics, as you see, has a whole lot of overlap with data sciences, but there are some methods in statistics that are not exactly conventional or like defined as data sciences. These are like, conventional statistical methods to deal with test of hypothesis and things like that. I don't think people want to call that data science because this is purely statistics, right? So these two fields, mechanistic modeling and statistical modeling, have significant overlap with data science, although they're not exactly data science, right? So this is the two fields that overlap. Now I'm gonna go back and go inside machine learning. The reason machine learning became more popular in, especially in mid-80s, was because if a subset of machine learning methods called neural networks became very popular. Neural networks show some really impressive capabilities, became popular, went through the hype, and they become like their importance and their capabilities were so over-exaggerated that suddenly they died again. Just like anything else, it goes through a hype. People, they just want to publish, get more grants, and everybody is suddenly doing neural network. And it had its hype period and became sort of a pariah. Nobody touched neural network. I remember at the time, you know, I published my neural network work, but in order to publish it, I had to give it another name, because if I said I'm doing neural network, people thought I'm one of those, you know, crazy guys who are insisting that neural network is the solution for everything, right? So I'm saying that the hype kills the idea. So it died away in, I would say, early 90s. But again, in 2005 or 2008 or something, some families of neural network called deep learning, which had the problems people were concerned about, even more of those problems in them, called deep learning, became popular, right? And again, there was some justification. One of the problems that neural network had was like, you need a whole lot of data to train the neural network. And by the time people advocated for deep learning, they made the argument that now in the real world, in the world that we're dealing with, because of like all these measurement devices, all the like things that, you know, internet is producing for us, we have the large databases that we need to train not only regular neural networks, but also larger neural networks. That made an argument that, you know, deep learning is the ultimate solution, which is wrong. There are some good capabilities in deep learning, but the fact that you see all these publications coming these days and they're just using deep learning and nothing else, that's another hype that in a few years people, I'm guessing, I'm quite sure that in a few years people don't even mention the name deep learning. So just think of the reality and the hype of all these techniques. Now, you hear some other buzzwords around. One of them, buzzwords not in a bad sense. It's a natural language processing, which is again part of artificial intelligence. It has significant overlap with machine learning because it's using some methodologies in machine learning and using some methodologies in statistics. Natural language processing was created to allow people to essentially analyze text data and to some degree analyze voice data through, you know, speech processing. And this has an impact on medical applications because, as you know, in medical applications, we generate a whole lot of text, unstructured data that needs to be sort of analyzed properly to extract the most important features out of them. So that's natural language processing. And then we had the field of computer vision that I put it entirely inside data science. And it has significant overlap with artificial intelligence and even machine learning, but it has things that are outside the field of, you know, data science, there's a field of artificial intelligence. And computer vision talks about how computer algorithms can analyze the concepts, the visual data that is proposed to them, right? That are given to them. Computer vision, which uses essentially the same methodologies as artificial intelligence, things like, you know, neural net and so on, it has significant overlap with another field, which is called signal image processing and video processing. Signal processing was a field that was created practically at the time that artificial intelligence was created, mostly by people in telecommunications. And it essentially, if we put signal aside, most of that image and video processing, they're part of computer vision, but they went beyond that. And I would say, as you see, part of this signal image processing goes even beyond data science. It goes to very specific types of mathematics that is used for this field. But I want to take a moment for all of us to just look at this diagram and put everything in one place in our thoughts. So when people are talking about machine learning and artificial intelligence, machine learning is a subset of artificial intelligence. Even in my writing, and you will see that in here, you will see in the same presentation throughout the workshop, that I am saying artificial intelligence / machine learning. What I mean is that the entire field of artificial intelligence, in particular machine learning. I'm not saying artificial intelligence is different from machine learning. Any machine learning is artificial intelligence. However, when I want to say artificial intelligence, in particular machine learning, I put AI / ML, okay? And so another thing is, like, again, a bad understanding and misnaming of, some things in the literature. They say that, are you using deep learning or are you using machine learning? What are you talking about? Deep learning is a type of neural network, which is a type of machine learning. When people say, are you using deep learning and machine learning, I have two understanding. One is that they don't know what they're talking about. Secondly, they think that there are things in deep learning that were not covered in machine learning, which is not true. That every skills, every technique, everything that you need to do deep learning is included in machine learning. If you learn machine learning, deep learning becomes like one special type of that, okay? So the same thing with natural language processing, misunderstandings about natural language processing. So person says, like, I'm doing natural language processing, not artificial intelligence, and I don't understand what they're talking about, right? I want you to pay attention to the fact that these things overlap significantly. And if you're referring to one particular method, one particular family of methods, you need to know exactly where they reside within this, like, this universe. Okay, so let's keep this. I'm saying, as I said before, that I may not be completely accurate with this diagram, but I think it's a good starting point for us to put everything in place. Okay, so having said that, I want to ask a very simple question, because this machine learning is a significant part of what we're doing. It's a majority of focus of everything that we do in this, like, workshop for data science would be focused on machine learning. So the question is, what is machine learning? Can we explain machine learning in simple, words and diagram? I'm going to use a diagram for that. Let's say this is the problem or the system that is not well known or characterized. Why am I saying, and why do I have a cross on that, saying like this is like inside you cannot see? If you know what is happening with the system, you better go use mechanistic models. If you know exactly what differential equations govern this system, you better not use machine learning. And I will get back to that. You know what you're doing. Why do you, ignore the knowledge that you have about the system? So if the problem is unknown, you don't know much about it. You may know some things about it, but you don't know much about it. You don't know it exactly. You get the system and produce some data from the system. Like, for example, look at the database of people going to hospital for a certain disease and diagnosis and the treatment given to them and the outcome, right? You collect some data from the system. Then you form a data set, structured data set that has input and output. Like, these are the treatment and this is the outcome. You have to define exactly what Brahmaji was saying is define your input and out, define your data, clean it up, make it a problem that machine learning can handle it. And then give it to a mathematical model, which represents machine learning, right? The core of machine learning is, the whole thing is machine learning. This is the core of that, which is a mathematical model. Mathematical model will try to relate the inputs, like the treatment, to the outcome, to the output, right? So mathematical model will try to model that, but you need to optimize it. You need to use the data that were given to you and some optimization techniques, some math magic to make the model better, to fit the data, right? It's just like fitting the data. It's like you get like, regression problem, you have some data, you form the model, you have to train it to form the model. Then you get an improved model because you try to optimize it. That's the part that majority of the failures happen, because at this point, they sort of claim victory and they start celebrating, and that's not right. When you have a model and you think you have a good model, that's the time to see how good it is and how to improve it. And in order to do that, you have to get some more data from the system and do a test and validation against some more real data and see how well the results generalize into a larger data set, larger space. And you may have to do this multiple times. As Brahmaji mentioned, don't just like celebrate too early. Like you need to go through multiple iterations, get more data, further improve it, test it again, get more data, identify the parts of the model that needs further enhancement or improvement, and then do that again and again and again, okay? That is essentially how you do machine learning. You rely on the data created by the system to create a mathematical model that emulates the performance of the real system, even though you don't know what the real system is, okay? So let's say, what are the goals? What can you do with machine learning? In the world of medicine in particular, normally when you do machine learning, you do one of these. You want to recognize and extract some pattern. You want to do pattern recognition. For example, you want to see what is the pattern of heart rate variability when people are becoming hypotensive, right? What happens with the variability of the heart rate? You want to explore some patterns associated with certain disease or certain complications. Or you want to do phenotyping. You want to say there are, this is a cancer, this is like, breast cancer, and we want to see what are the types of breast cancer. Depending on the data that you collected, you divide the population into phenotypes and subphenotypes. Then you want to do predictions. You want to predict that this patient with this data is going to have some complications. You want to make a prediction even in time. You want to make a prediction. One of the things that Mike Mattis is doing is working on technologies to predict in 1 hour, 5 hours, 10 hours, 12 hours, the person who's recovering from a major cardiac surgery is going to have an event, right? Make a prediction that in 12 hours, the person is going to have an event. Those are highly, these are very important things for medicine, to have the ability to predict what is going to happen in the future. So again, prediction is different from detection. You can detect that the person has a complication, a disease by itself. It's variable. It's a valuable thing to have, to say that the person has that disease or complication. But prediction is talking about future, right? It's not saying now, it's saying like sometime in the future. And you can both of them with machine learning. And eventually, you want to form a prediction, recommendation. For instance, you want to say that this treatment will help this patient better than that treatment. Is this a time to do a surgical intervention? Is that the medication that we want to give to the patient? So machine learning can create recommendations that are presented to the clinician, and clinician makes a decision. I want to emphasize something in here. We have to be very clear, because of all the things that we discussed in the past, all the legal, ethical, everything aspect of that. We are not talking about, most of the time, not always, but most of the time, we are not talking about clinical decision-making by the computer. We are talking about computer-aided clinical decision support system. In a way that I interpreted, you create the recommendation, prediction, estimation, phenotyping, patterns. You present them to clinician and let the clinician decide what to do. So you're saying that, and this is a tough thing if you are a clinician using data science, because You want to form your own decision, but you're looking at the algorithm to tell you what is your decision, right? You're creating an algorithm to tell you what the decision might be, right? So those are delicate legal, ethical issues that I'm not an expert to handle that, but I can safely tell you in other fields that I've been involved, in financial world and in other things, these things get to a point that become completely resolved or not resolved. People put everything in place to have a cohesive and justifiable system. But for now, for many parts of medicine, this is still being defined. So what I prefer to call these methods are computer-aided decision support systems, okay? So majority of what you see in machine learning is inspired by biology. Remember, I told you about, in last slide, about neural networks, which was like, sort of a major factor in making machine learning popular. Neural networks were simply inspired by basically biological, physiological neural nets, basically. What is happening inside the brain. And people who actually define these things, they were studying neuroscience in order to create machine learning. Essentially, back in 1970s and 1980s, we had a whole lot of machine learning algorithm, but the performance was not getting close to the performance of a human, right? Simple thing as crossing the road. You want to cross the road, we get all the data that human has, all the videos and sound and everything. You feed it to some machine learning algorithms that they developed up until 1970s. And they were comparing the decision that the machine made with the decision that human made. Humans like very easily can see, oh, the car is too far or too slow, whatever, or too fast or whatever, they make a decision. But these machine learning algorithms that we had by that time, they were highly sophisticated. However, the performance was not even close to human decision making. So the humans were making far better decisions, far more accurate, far more defensible sort of decisions and performances. Because of that, people thought perhaps they should start thinking about using a different type of machine learning that is emulating the performance of the human brain, because it's the secret and everything was the human brain, right? Human brain was the difference. People who were trying to sort of save machine learning, they studied the neural network inside the brain, and based on that study, they tried to emulate the performance and the interaction between neurons, and they created the field of machine learning, neural network. So I want to re-emphasize the fact that in reality, majority of these machine learning methods are inspired by biology and more specifically by human physiology. Now, recently, there are some machine learning algorithms that are inspired by immune system, which is also a very, very interesting part of the field. But what I want to say is that we emphasize the fact that unlike this mechanistic modeling, that you use the physical laws that govern the system, in machine learning, you don't need these physical laws. You just get some data from the system and you emulate the performance of the system. So now I want to emphasize the differences between like these AI, ML, artificial intelligence with emphasis on machine learning versus statistical analysis versus mechanistic modeling. I put these, start with the statistical analysis and mechanistic differential modeling, differential equation modeling. If you know the system exactly, there is no point to do anything but differential equation. You know the physics, you know the laws of physics that govern the system, you go do that. If you have absolutely no idea about the system, you have no knowledge of the system, and you want to have a simple solution, you do a statistical analysis. That has been the case before machine learning showed up. And this has been the solution that I think still people should follow. If you know the equations, go for mechanistic modeling. If you don't know anything and you don't have a lot of data and you want to have something simple, go for a statistical analysis. Now, where does machine learning come? Here's a compromise This is machine learning is the compromise between these two words. Machine learning resides somewhere in between the cases that you need to use differential equations or you need to use a statistical analysis. In these cases, you have some knowledge of the system, some limited knowledge of the system, but you don't have the differential equations that govern the system. You know a lot about the system, not exactly the physics that governs that. But at the same time, you have some data from the system that, just like a statistical analysis, wants to make a prediction or analysis based on the data. That's where you use use artificial intelligence or machine learning. So if you don't have enough data, if you want to know more about the system, not just a statistical analysis, avoid that statistical analysis. If you have differential equations, if you don't have differential equations to govern the system, avoid that and you stick to artificial intelligence and machine learning. Because of that, I can tell you that now we are living in a world that this space in between a statistical modeling and differential equation modeling, mechanistic modeling, becomes wider, and there are far more applications in which you can use machine learning for. And this is why machine learning has become a major, aspect of practically anything that we do in the new life. Starting from all the cell phone stuff that you're using, all the way to autonomous driving system and everything. Machine learning is getting into that because this is space between a statistical analysis and mechanistic modeling is 90% of what we're dealing in our life, not even more than that. And machine learning uses techniques from statistical analysis. It uses a whole lot of statistical methods, so they have some overlap with the technology, with the techniques used in statistical modeling. And it uses a whole lot of differential equation as well. So in reality, you're dealing with a methodology that is essentially using the good things of the two worlds that are residing on the extremes, okay? Now, let's talk about some overall, approach to using machine learning for health applications. One is that you start from raw data. You have some raw data. You identify physiologic signals, biomedical signals, like electrocardiogram, or if you have genomic sequences, that's also signal. Some genomic sequences. You do signal processing to extract some features. These signals may be very long and they have a lot of repetition and have a lot of non-informative and noisy stuff in it. You have to use signal processing to extract what is important. For instance, heart rate variability, the things that are important, you extract it. Same thing with images and videos. You do image processing and you extract what is important. What is the presence of a tumor in an image, size of the tumor, like the shape of the tumor, texture of the tumor, things that are important as opposed to like every detail in the image. Then you get clinical notes. You use natural language processing to extract, some features, some understanding of what the note means. If the note contains like person saying a tumor of like at this location or whatever, those natural language processing would extract from us. Then you have demographics, lab results, medications, all the other patient information, and you do a statistical analysis and you get the features out of that. Then you have an integrated feature database. Integrated feature database means sometimes we have to put these features on top of each other and then compress it to have a smaller representation. Then you get these compressed features into artificial intelligence or machine learning method, which gives you a bunch of recommendations and predictions. That is essentially the whole story that we're dealing with. Like, regardless of the specific application, this is what is happening in real world. Let's look at some examples. For instance, consider cancer decision support systems. They look at a bunch of images. They use image processing to analyze check the presence of tumor, size of tumor, stuff that we talk about using a neural network. Then they use genomic signature, analyze it with some statistical method to get some genomic signature of the data, features from the data. Then they integrate all of these with some machine learning method. Let's call it support vector machine. You can call it SAM or theme, whatever. We talk about this later on. We use some machine learning method to integrate all these features and predict whether this is like, benign or whatever. If there's a tumor, it's benign or cancer. And if it's cancer, what level of cancer we're dealing with, and so on and so forth. Take a look at another example, like trauma decision support systems. You get a bunch of physiologic signal like electrocardiogram, PPG, ABP, all those things that are coming from monitor. Then you get a bunch of CT images that happen, that use a lot in trauma, and they use computer vision image processing to extract features. And then you use like a machine learning method, let's say random forest, to integrate all of these to predict something like survival, number of days at ICU, the likelihood of readmission in 30 days, and things like that. This is a regular, machine learning applications, typical scenarios that people use in this world. But remember that machine learning, that artificial intelligence and data science is not just this like a small portion of, like neural network, random forest things that we're talking about. There are other entities, there are other types of machine learning out there, which I'm going to talk about them very quickly. And you will see that I have integrated them recently into the curriculum for the bootcamp as well. One of them is agent-based modeling. What is agent-based modeling? We want to simulate or emulate an environment, a system. We define an agent, and that agent has some data, memory, and some function. For instance, a bird, like let's talk about like a non-medical application. A bird has some memory where the nest is, capture some data, like they see the aerial images of the area that they're flying in, and they have certain functions. Go find food, breed, or whatever. Stay away from bigger birds. They have certain functions and certain memories. In order to function, they need to be able to interact with the environment. So basically, see the environment and go make a nest in the environment, and so on and so forth. And they have to also interact with other agents. They have to work with other birds. If they're migrating from one point to another, it's not that they migrate individually. Every single one of them may get lost, but if they're flying together, a flock of birds, when they're interacting with each other and they're guiding each other, they're far less likely to fail. They do the migration. So this is the core idea of agent-based modeling. Now, if you want to put it in a real application, all you have to do is get an environment and throw a whole lot of agents like that and let them interact with each other, right? Just like the flock of birds that I told you. Like you have like an ecosystem, there are so many birds, they interact with each other, and because of the interaction, they populate the area and they grow. What are the types of agent-based modeling that you might have heard of? You have heard ant intelligence. There's like so many types of these. Ant intelligence, saying that every single ant is nothing, but together they can build huge things, and they do sophisticated functions because each one of them is an agent, doesn't have a lot of capability, but communication with each other and environment allow them to have significant capabilities. Swarm intelligence, you heard that. Bird flock intelligence, you heard that. You have heard so many examples of agent-based modeling, which unfortunately it's underused in medicine. And I can tell you some biomedical applications that people are doing as we speak, but not enough. One is drug design. What is drug design? Is in order to do drug design, you need to simulate or model the interaction between a number of molecules, agents that are drugs, with another set of like entities that you can call them environment, that are targets, the receptors on the cell, right? Remember, majority of what you've seen in conventional like biochemistry things is that you get one molecule and one receptor, and then you talk about like how they bind with each other, all these things. In reality, you have a soup in which, like with Brownian motion, millions or billions of these are interacting with each other. That is the concept of environment in which the agents are interacting with each other. Another example, epidemiologic modeling. In epidemiology, the objective is to find like the growth of like a pandemic, for instance, like we're dealing with that right now. So what they do for the modeling, they consider each patient carrying the disease as an agent, and the environment is like, people that they're interacting with, the places that they go, and they run simulations to predict how this interaction is going and how fast the pandemic is growing and where they go. And again, cancer modeling. Remember that the tumor is nothing but a bunch of cells that are interacting with the environment with the other cells. Again, there are so many things that, simulations that people do with that regard. There are, I think we're gonna go, if you don't mind, we go like 10 minutes, 5 minutes beyond the time. We can start later to compensate that. It doesn't, no, we can, I will try to finish it quickly. The another family of functions that are useful, but they're underused are fuzzy models. Remember that most of the machine learning methods are non-transparent, like, deep learning, neural network, whatever, you cannot share the knowledge in the model. More importantly, physicians cannot inject their knowledge into the system. Neural network are initialized randomly. All the weights are sent randomly. But in reality, clinicians have very good gestalt, whatever intuitive understanding of what is happening in the system. Why not use that knowledge to improve the performance of the system? And this is like, but the issue is that clinicians have the knowledge that is explained in crisp way, saying like, if the heart rate is less than that, or if the patients, let me give an example. If the blood pressure is very low and the heart rate is very high, then the person is likely to get hypotensive, right? It's a knowledge that is not explained in very accurate numbers. This knowledge is there. How do we use that? How do we implement that in reality? How do we create models based on the knowledge that clinicians have? This is the act of fuzzy logic. I'm not going to go over the details of that. I have the slides in here for you if you want to study them. But I am saying that there is a group of methodologies like case-based reasoning, fuzzy logic, approximate reasoning. All of these are methodologies that allow you to get the knowledge from the expert, the clinician, initialize the model, optimize it with data, and then give clinician not only the prediction, but also improved knowledge that they had. They were not quite sure about these things. But using data, the methodology optimizes these methods and give it back to them. And not only that, it can extract rules understandable by humans that they were not, included in the original set. They were sort of not discovered by the humans. I'm gonna skip some of these because I don't think we need the details on that. You can study that by yourself. This presentation will be made available to you guys. So our plan in this training is to cover some standard methodologies in machine learning, like naive Bayes, regression methods, support vector machine, and so on and so forth. But we also talk about the other methodologies that are underused in artificial intelligence, in data sciences, and we talk about those as well and provide some examples of that. Like I said, I have 2-3 slides that I jumped over that they're talking about details of fuzzy logic. You really don't need them, but if you wanted to study them, you can certainly look into that and get back to me. I think that's the time that we stop the morning session. We have 1 hour for lunch, and we continue at 1 o'clock. Let me stop sharing. So again, James, we're going to just mute and come back at 1 o'clock, right?
Absolutely.
All right. Thank you very much. Talk
All
to you
right.
guys soon.
Perfect. See everyone then.
Everybody is back. I gave an introduction at the beginning on all the speakers, including Dr. Shoding. But again, it's such a pleasure to have Dr. Shoding here with us. Dr. Shoding is one of the stars of medical school who has, integrated data science perfectly into his research. I can tell you that few years ago when he got his K award, the score was, I think, Mike, was it 11?
You don't have to say. It's not.
No,
it's not important.
The score was something like unprecedented. I had not seen like such a positive review by the panel. And keep in mind that the panel was mostly, clinicians. There were some data scientists in it, but and Mike was putting all kinds of equations and ideas in the proposal. And I think that was essentially a document that shows how people can be, how clinicians, clinical researchers can be successful by properly integrating data science into their proposals and works. And he's been creating so many, fantastic results based on the methodologies that he's been implementing. And you heard from Ajay about the collaboration that Mike had with Jenna Wins, Dr. Wins in computer science, and they have produced so many grant proposals that most of them have been funded, if not all of them, and they have like multiple papers on highly sophisticated data science applied to highly sensitive clinical applications. So Mike, thank you very much for accepting to give a talk. And also remember that Mike is also giving lessons he's teaching during the boot camp as well. Mike.
Great. Well, we'll start it from the beginning. Thanks to everyone who's sticking around to listen to this workshop today. I think in planning of the workshop, one idea was to provide participants an example of, folks who've been in this space for a while, particularly clinicians who have moved into data science and what they've done. The field is super broad and you can do many different things. And so I think the idea here is I'm going to share a little bit about what I've done in this space, and hopefully it will inspire you to think about what a contribution you could make in this space with your particular clinical application or clinical interest. So with that, my talk is data science for clinical diagnosis of the acute respiratory distress syndrome. A bit of background about myself, because I think that's also useful. So I came to the University of Michigan in 2012 to complete a pulmonary and critical care fellowship. And I completed that fellowship in 2015. And I was pretty heavily involved in research during the end of my fellowship and the beginning of my career here, and also received a clinical research master's degree in 2016. And I want to say that I thought that background was super valuable as I got into the field of data science, because I think I came to this field with some really fundamental understanding of concepts in epidemiology, including study design and confounding and these types of things that I think have really served me well. And prior to getting more deeply into data science, my work was largely in studies of health services research. This is basically studies about how we deliver healthcare, how we evaluate the quality of healthcare, and my work primarily used healthcare administrative data. These are large billing data sets. But around the time that I was thinking about writing a career development award, my interest in data science grew, largely because what I wanted to do ultimately was like improve care for patients with acute respiratory diseases. The data and the sort of methods that I knew were really not quite aligned with those goals. And so I ended up writing and was awarded KO1 from the National Heart, Lung, and Blood Institute in 2017. A KO1, there's three types of K awards: K23, K08, and KO1. And a KO1 is a special award that NHLBI really used to focus on particular interests. And at that time, they had a big interest in supporting people to receive additional training in sort of the space of clinical informatics, machine learning, and data science. And so that's the reason why I approached that route. And as part of this career development award, I needed to have mentorship. And the mentorship for this award worked out really nicely because the award sort of tried to bridge both, clinical research in ARDS with data science and machine learning. And so for my award, I had a clinical research mentor, Jack Awashina, and then a primary data science mentor, Kayvon, who you've all gotten to know this morning. And so I did get that award funded. And then what did my training look like in data science over the next few years? Well, I did audit some coursework, the Introduction to the Machine Learning course in the electrical engineering and computer science. And frankly, much of that course was over my head, but I did participate and went to class and sort of listened and gleaned as much as I could. And I also took a bioinformatics course that Kayvon taught. But in addition, I just really got my hands dirty. I read a lot. I worked really hard to understand some of these methods and approaches. I taught myself a lot of coding along the way. I actively participated in lab meetings from sort of mentors and collaborators. And then ultimately I've been able to establish really strong mentorships and collaborations with folks with technical backgrounds. And I think that's really served me well. So my initial sort of getting into this space was focused on the acute respiratory distress syndrome. So ARDS is acute diffuse inflammatory lung injury that occurs in patients that are critically ill, like with pneumonia and sepsis, trauma. And when patients develop ARDS, it requires an intentional and aggressive approach to management. The problem was that we knew right around the time that I submitted my K that even though we all know that ARDS is important, it's really under-recognized. And as a consequence, patients aren't receiving therapies that we know improve outcomes. And why is this hard? Well, there's a lot of reasons why this is hard. This is hard because clinicians are busy in clinical practice and sort of they don't pay attention or miss things, but also it's hard because ARDS is sort of like this fuzzy thing. It doesn't have this clear gold standard for, oh, this is ARDS, this is not ARDS. It's a set of clinical criteria like sepsis. And even among physicians, sometimes they disagree about who has ARDS. And so identifying ARDS is a hard problem. And so I sort of wanted to get into this data science space, sort of thinking about how can I help the field in this problem of improving the precision or reliability of identification of patients with ARDS. And I would say that, to take a step aside is sort of framing the clinical problem and what you can actually do to support that clinical problem with data science is a really important first step, right? It's like having a clear problem that you want to address is really important, and why you're going to address it. There's many times when folks in this space are working on clinical problems or that maybe aren't that ultimately that meaningful. Prediction of mortality in the hospital, while it sounds important, really isn't going to influence care that much. So it's really important to find a clinical problem that sort of aligns with the data science tools that you have, and then ultimately will have an impact. So, like I said, diagnosis of ARDS among physicians is sort of variable, and so I was hoping that we could use data science approaches to help physicians with the diagnosis of ARDS. And in addition to helping physicians identify ARDS in real time, what else could we do with tools if we had data science related tools to identify patients with ARDS? Well, we could also be smarter about how we evaluate ICUs. We if we had tools to identify patients with ARDS, we could evaluate how ICUs are performing and help them get better if they're performing poorly. And then also, another important area here is the fact that we have these increasingly large biomedical data sets and translational data sets, genomic data sets. And it's not trivial to take, a data set of 1 million patients and figure out which among those patients developed ARDS. So if we had tools to help us do that, that could be really exciting. In addition, if we had such tools to enroll patients in clinical trials, if we wanted to enroll patients in ARDS clinical trials, having automated data science type ARDS tools to do such could be really powerful. Just as a side here, at University of Michigan, we don't always deliver great ARDS care. ARDS patients should get low tidal volume and ventilation, and ARDS patients, when they are severely ill, should get prone positioning. And you can see that our numbers here are not ideal. Here's an example of pragmatic clinical trials or large genomic databases that these types of tools could be used to really accelerate and empower research. And here is a statement by our American Thoracic Society about benchmarking ICU performance in ARDS and the potential need for automated tools to help identify ARDS patients. There are some ARDS type tools out there. And so again, when I was thinking and writing about my K, I had to sort of acknowledge the fact that people have been working in this space, but they were really very simple tools that relied on analyzing and searching for some terms in a chest X-ray report and looking to see if a P to F ratio was below some certain threshold. And I thought that we could do a lot better if we built tools with a richer set of data that would ultimately have higher accuracy and do a better job of detecting ARDS patients. So I don't think we've actually shown any math or any notation yet, but I wanted to show you this just to demonstrate that me with an MD behind it, their name can talk a little bit in math and notation. What we're trying to do when we use machine learning for ARDS detection is really a scenario where we have a group of patients, and that group of patients is represented as I from 1 to however many we have. We have some characteristics about these patients. These are the X's, and we have information about whether or not they had ARDS. That's the Y. And ultimately, what we were trying to do with machine learning here is develop something that allows us to map the characteristics, the X's, to that Y, whether or not ARDS is present. And this is, a traditional classification task. So the first sort of thing that I wanted to get into is, can we develop an EHR-based model for ARDS detection? And I wanted to ask, what's the incremental value of various EHR data types? And then what's the performance gain with a complex machine learning model compared to a simpler linear or rule-based model? This is a hard problem, as it turns out. If I were to go back 4 years and work on this again, I think I would, but I would come with eyes wide open about how hard it is. We are significantly limited by the data that we have. These types of approaches need a lot of data. And in my particular approach, which was detection of ARDS, we had a lot of data at University of Michigan, but we didn't have really highly accurate outcome labels, like does the patient have ARDS or not? So ultimately, to accomplish this work, I had to sort of pay or cajole a group of physicians to go through a number of hospital charts and review patients for ARDS. Do they have ARDS or not? And so over really the course of a year or two, developed a training cohort of patients, about 1,800 in total, that were reviewed by multiple physicians for diagnosis of ARDS. And among those patients, about 350 actually developed ARDS during their hospitalization. And then, we had to also have a holdout test cohort to determine whether the models that we trained are actually valid by testing them in an independent cohort. And we defined this cohort temporally. So these patients were hospitalized in a different period of time. We looked at 500 patients, about 500 and 95 who developed ARDS. And these are the types of structured data that we looked at. So we looked at vital signs, laboratory results, respiratory support information, medications, clinical notes, and also radiology reports, which I'll get into. I think one of the key things about data science is a real focus on additional and analysis of more novel data types, maybe data that we wouldn't have traditionally been comfortable analyzing in traditional statistical analysis. And one of these is information contained in so-called unstructured or text-based documents. Here's one more little bit of math that I want to show the participants, because just to show everyone that, again, a clinician can talk a little math, and to also show that this isn't as hard as it seems. So, the fundamental model that we use in this analysis is a logistic regression with regularization. What this is showing here is that we're basically going to take all these features, characteristics about these patients, X1, X2 through Xn, and we're going to try to learn a way in which we combine these linearly and then use some sort of nonlinear transformation to estimate the probability of ARDS. We're going to estimate based on some characteristics about the patient, the probability the patient has ARDS. But at the same time, we know that if the model sort of learns overly detailed information about our training data, sort of overfits to sort of all these nuanced characteristics of the training data, it's probably not going to work well in a different setting. So in addition to sort of learning like the optimal beta coefficients here, these optimal linear combination of weights, what we also want to do is minimize the total amount of coefficients that we use. And so this is the so-called regularization approach. And that's the main analysis that we performed here. The other sort of nuance here is that when you're dealing with clinical data, it's not really just a single point in time, right? Like over a patient's hospitalization, you actually have lots of data over time. So that's another nuance of this analysis that's interesting. So, over a patient's course of illness, you may imagine having an estimate of their likelihood of ARDS that might change. So how do you evaluate a model in this setting? Well, one way to do that is to define a pre-specified probability threshold. And as soon as a model probability reaches this threshold, we say now that this patient has been detected as having ARDS by the model. And if the model predicts a certain time of onset, and you look at that compared to the actual onset, now you can start to measure performance metrics such as sensitivity, specificity, positive predictive value, the area under the receiver operating characteristic curve. And then you can also look to see how close the model was to when the actual time of ARDS onset was. The other thing that I mentioned already is, how can we incorporate text features into such a model? So, clinical notes in the chart looks something like this. This is an example of a chest X-ray report written by a radiologist. How do you encode this as a set of data characteristics or features, something that a model can ingest? And so to do this in work, I used a program called CTAKES, which is sort of a well-known way to handle unstructured data that's been generated in healthcare. And in particular, what I use the CTAKES for is for identifying and accounting for negations, in clinical notes. Sometimes things that are documented are explicitly documented as not present. So no infiltrate. So you don't want the model to think there's an infiltrate if in fact the word before it was no. And then also this CTAKES also has a method for sort of taking synonyms of different words into the same, combined into the same sort of concept. And here I'm just showing an example of, if there's a concept called the acute respiratory distress syndrome, we may use synonyms in electronic health record data. And so that is what we use CTAKES for here. And basically what we found is, like, as expected, when you use more and more complex information from the electronic health record, you get a model that can perform better. So if all we had was vitals and labs, we get an AUROC of 0.85. So AUROC is on a scale of 0.5 to 1. So 0.85 is not bad, but you can see as you sort of improve, if you enhance the model with providing it more information, more characteristics about the patient, it can do a lot better. And you can look at the types of variables that the model really weighted heavily. And you can see that, that these variables are sort of what you might expect when you want it to make a decision about whether a patient has ARDS. On the other hand, one other thing that we did here is we asked, gosh, that more simple linear model that was regularized logistic regression basically just takes a linear combination of all those different characteristics to make a prediction of the probability. How does it do compared to these much more complex modeling approaches? So we looked at these other approaches like support vector machine, random forest, XGBoost, recurrent neural networks, much fancier modeling approaches, and found that, honestly, it didn't make that big of a difference. So a simpler linear model that's potentially much more interpretable performed just as well as these more complicated models. And so that's an interesting finding that I think Kayvon is always excited about seeing, that sometimes simpler is simply better. And then when we took this final model and applied it to the temporal holdout data set, we found that, it continued to perform pretty well. And, these are some sort of visualizations of that in performance in the test cohort. And data I'm not showing you is we actually can put the model head to head against individual physicians who are also reviewing patients for ARDS, and found that, the model is performing pretty good relative to individual physicians, suggesting that really, if it could be put into implemented in practice, it may actually be really helpful, and that those are things that I'm thinking about now. Just another visualization that's interesting. Again, when you're operating on this time series scale, you can see how the probability of ARDS changed over time. The black line here is when physician reviewers thought the patient had ARDS, and the blue and the red line shows these models what was the probability that the model thought regarding ARDS. And again, the complex model, which includes more detailed information like all the notes, actually lag behind the simpler model. So what are we going to do next with this particular machine learning approach? Well, one important goal is to validate these algorithms on external cohorts, and these types of data are becoming available, and I'm working on doing this in the MIMIC4 data set, which is a publicly available ICU data set. Still need to demonstrate the feasibility of using this type of algorithmic approach to identify patients prospectively or in a research setting like in a genomic data set. And really, I think one other question here is understanding the characteristics of patients with these physiologic signatures. So we found that we built a model now that physiologically identify patients based on labs and vitals with ARDS. Why is it the case that sometimes these patients weren't actually annotated or scored as ARDS by clinicians? So what does the clinician know the model doesn't know, or is the model telling us something new about our understanding of ARDS patients? So I wanted to add this also because, this is sort of, data science 101, the types of things that I showed you. But, the problem of detecting ARDS is more complicated. And so because it's a little bit more complicated, there's lots of opportunities. I find working in this space for a while and working with really smart technical collaborators is when we work together on things, we can potentially advance the field of data science, working through nuances of a clinical problem. And so for ARDS, that meant accounting for things like uncertainty and privileged information in detecting ARDS. So just as a step back, in machine learning, particularly in classification, what we're trying to do is to give an algorithm a set of training examples. And that algorithm's goal is to find a function among all the potential ways that you can map those characteristics to a probability of ARDS that best approximates some optimal decision rule that will ultimately lead to really well-performing algorithm. So, but when we as humans learn something new, we learn by example, but we also have a lot of sort of extra information that we could utilize. So we don't need to learn with a lot of examples. When I learned how to care for patients with pneumonia in the hospital, I didn't need to see 1,000 cases of pneumonia to get good at caring for pneumonia because I had a supervisor physician to help us, to help me with learning how to care for these cases. I went to UpToDate to read about it. I had all this other contextual information. So this is the idea of this extension of machine learning for ARDS. And so in particular, with Kayvon and I were thinking about this concept called privileged information. Additional information that you can use to help a model at training time to improve their ability to learn how to detect ARDS without a ton of examples. Because, like I sort of told you earlier, building up a data set like this was really hard. It took a long time to build a large data set with annotated examples. And so that was the idea about this work. And so now, instead of training examples where you basically have characteristics and a label, you have a bunch of other information. For a training example, you have information about their characteristics. You might have other information about the patient that you can use to help teach the model how to make a decision about whether a patient has ARDS. And then also, in addition to having that label, whether ARDS was present or not, we can also provide the model interesting other information like, okay, we think it's ARDS, but gosh, we're just really not that sure because the data is sort of noisy or there's still uncertainty about this case. So, can we teach the model that, yeah, this is probably an ARDS case, but gosh, we just have lower confidence in that assessment. And so using these approaches, we've published a couple of papers now in this space about incorporating things like uncertainty and privilege information in detecting ARDS. I want to also tell you about sort of one other thing I'm working on in this space, just to give you, again, a flavor of all the types of data and all the types of approaches one can use for identifying patients or sort of working this space of detection of ARDS. And so that is sort of approaches for improving or detecting features of ARDS on a chest X-ray. So what I just talked to you about a second ago, was all these EHR-based models that I've worked on developing for detecting ARDS, but these have some limitations. So for example, what you saw was that the best performing approach used radiology reports and clinical notes. And that might be a limitation, right? Because one, if we need clinical notes, we have to wait for those clinical notes to be written by a physician. So maybe we've missed the window. So also, if we ever want this model to be used outside of University of Michigan, we don't want to learn any sort of nuances and how University of Michigan faculty or residents document things in their notes. So maybe training on clinical notes may limit generalizability. So gosh, you know, this chest x-ray seems really important in detecting patients with ARDS. Can we train a model to detect ARDS based on a chest x-ray? And so there's a really, really exciting work in this space. You know, Kayvon gave a lot of background on neural networks and deep learning. And, you know, I entered this space with a lot of skepticism, just like Kayvon, because I think that's very important to have healthy skepticism and also recognize that, you know, these types of models, you know, have so many different parameters that one has to learn. So it's so easy to overfit these models. Nonetheless, you know, there's been a lot of exciting publications in the space about models that can use medical images to detect diseases. This is just an example of a model that analyzed retinal images to detect diabetic retinopathy, or a model that looked at skin pictures to detect skin abnormalities and malignancies. What are these deep learning models doing? Really what they're doing is over layer and layer and layer, they're taking an image and abstracting it into sort of more and more abstract features that ultimately can be used to classify an image, whether it's a male or a female, or whether or not a chest x-ray is consistent with ARDS or not. So the key idea here is that you take an image and over multiple layers, transform pixels into variables that can be used for classification. And so I've been working in this space with a number of different folks. And in one group, we have now trained a deep learning model to detect ARDS with really high accuracy and impressive accuracy that's equivalent or better than individual physicians. And when you look at, you know, what the deep learning model is paying most attention to, what you can see is that it seems to be focusing on portions of the image that are consistent with actual ARDS. So this is, again, a promising, and it could potentially really be helpful for our field. But again, I approach this with a substantial amount of skepticism, and this approach would need to be validated and ultimately would be needed to be implemented in a clinical environment to find out if this is really sort of something that's going to improve patient care. So I'm just going to wrap up. I'm a little bit early, but I'm sure everyone won't mind. And it looks like Michael Mathis is already on. So once I finish, he can go next. So how has data science helped me in my research career? You know, I hope I've shown through this work that I've presented in front of you that these tools do offer promising solutions in ARDS detection. And I would also say that a lot of the knowledge that I've gained working in ARDS has really equipped me to address many other related problems, not just ARDS, but diagnosis of acute respiratory failure. I've talked with folks about diagnosis and treatment decisions for asthma. And, you know, so far, I would say that grant funding agencies have been very, they've perceived this work as valuable, and so have been able to get competitive grants from a variety of different organizations in this space. And then I would also finally say that I'm still an MD. I didn't get a PhD in computer science or engineering or some other related field. So my work has been substantially enhanced by ongoing collaborations with technical experts. And I plan to do that for the rest of my career. I don't plan on going it alone anytime soon. So thanks very much. With that, thanks for listening. I'm going to hand it over to the other Michael, who I think is going to talk about data science and anesthesia.
Thank you very much, Mike. It was fantastic. We really enjoyed the I mean, I'm glad that you explained everything from the point of view of your research and your career and how you started and how you approached it. That was really exactly what we were looking for.
Great.
Thank you very much. So if you have questions for Mike, I think, what do you prefer, James? You want to leave it for the Q&A at the end?
You know, let's yeah, if we, I think we'll have a little extra time since Mike ended a little early, so let's let Mike Mathis wrap as well, and we can take the Q&A from there.
Okay, fantastic. So thank you very much, Mike Shoding. And now Mike Mathis is another star in the medical school, also a person who has integrated all kinds of computational methodologies and technologies, not just computational methods, technological, sensing devices and things like that, getting data from the monitors and incorporating them into decision making. And Mike is by undergraduate training, it was in engineering. So biomedical engineers have understanding of both sides, by the training. But I can say that during these years that we've been working together, Mike proved to me that the most difficult problems in medicine, he has the ability to simplify it and map it to data science. I can tell you, as Brahmaji mentioned, the main thing, one of the most difficult parts of doing any data science for clinical application is to make the clinical application, clinical scenario, something like process it, simplify it, and make assumptions so that in the end you have a data science problem out of that. Clean up the data, think about what is input, what is output, what is the label. For one of the applications, and Mike will probably mention that, for one of the applications, Mike worked, formed a sort of a panel of clinicians and worked on definition of what is like an event in cardiovascular world. And like, it took us probably a year or so to come up with a definition that was acceptable for all people. Then we could label the data. So he's a great leader for the community, and I'm very, very happy to and fortunate that he accepted to not only give a talk today for the workshop, but also he will be one of the instructors in summer. Thank you very much, Mike.
Thanks, Kayvon, for that very gracious introduction. Can you guys hear me right now, by the way?
Yes, and we can
Great.
see the slides as well.
Awesome. Okay, you can see my pretty face and see my slides. Fantastic. Thanks, Kayvon, for that very gracious introduction. As Kayvon mentioned, I'm a cardiac anesthesiologist here at Michigan Medicine. Have a research focus on using data science techniques to improve clinical care. My talk will be somewhere in between what Mike has given us with getting into the deep content of very specific projects. Somewhere in between that and what Brahmaji kind of did this morning with a broad overview and kind of the hypes and hopes of machine learning. Certainly have had some successes and failures that I think are interesting to go through. And I want to highlight a few of my own projects, and I want to highlight a few other projects within the realm of anesthesia, and getting at this issue of, I think one of the hardest things to do, and really what is much of the focus of this workshop and the course next year will be bridging the gap between a informatician and a clinician, and writing a paper in a way, doing one of these data science-based projects and writing a paper for a clinical journal in a way that clinicians can relate to, and it does not get into too much technical jargon, but does rigorously report your findings and make your methods reproducible. It's a real challenge, and something that I've worked to perfect along the way. Certainly have room for improvement there, but that's kind of what we'll focus on today. It'll be just a potpourri of a couple different examples of both my own work and the work of anesthesia colleagues, and how they illustrate different challenges, successes and challenges to implementation in clinical care. I don't have any personal conflicts of interest. I have grant funding through the NIH and Department of Defense. Here's my contact info. Feel free to email or tweet at me. And so what I think is important to focus on in a lot of these works is just preparing yourself for a conversation with clinicians who might have varying levels of familiarity with machine learning. And I think I might even be optimistic when I say varying. Most clinicians have basically no familiarity with machine learning applications, or their strengths and their limitations. And the ones that do can be very skeptical, and that's important. And Mike Schoeding, I fully agree that a healthy sense of skepticism is very important. It underscores the importance of making the case to a clinician who may not be a machine learning expert why they should care about this. And so then after establishing that kind of problem space, I want to talk through some real examples of my own work and work of others, some successes and failures that anesthesiologists currently or in the very near future will be using. And for each example, I'm going to go into some of the detail, but I really want to use each example to highlight different dilemmas, logistical, social, ethical dilemmas that each project has to address and what they can do about them. And so that's going to be the overview of this talk. So just focusing on setting the stage. The first thing I found is just clarifying what we're even talking about. And Kayvon gave that extremely informative overview of all the different, the Venn diagram of all the different data science terms, and it becomes just a mishmash, and the terms get conflated very easily. But I think it is important to when you're embarking on some machine learning project to just focus on what exactly are we even talking about. And so there's 4 different types of artificial intelligence, ranging from simple to complex. On the left-hand side of this, you just have reactive AI, and that's AI that has no memory, is task specific. An example is Deep Blue, the IBM chess program that beat Garry Kasparov in the 1990s. We have limited memory, and that's kind of where we're at today. Is this level of AI where they use past experiences to inform future decisions, and they're still narrowly scoped, but do have memory, and because of their narrow scope, can be vulnerable to outliers or new situations. So this issue of generalizability can become an issue. But that's where we're at today. Google self-driving cars is one example of an AI type that uses limited memory. And then beyond this, it's helpful to inform, when you're having conversations with clinicians to establish that you're not talking about these things that are way off in the future. This type of AI, a theory of mind, which is it's a psychology term, and when it applies to AI, it means that it's a system that will have social intelligence and understand emotions and can learn from few examples because it understands human motives and intent. And then there's on the far right, the self-aware AI, and that's again, those are light years away. So I just try to get everybody on the same page about what we're talking about when we're focusing on a AI application for healthcare, and it's really this limited memory focus. It's important to clarify what the goal is. It's helpful to reiterate to clinicians that the goal is to use data science techniques to improve care, to achieve a level of care that a clinician couldn't achieve by themselves. It's not to replace a clinician. That's a term called the fundamental theorem of biomedical informatics that was coined by Chuck Friedman, who's a faculty here at the University of Michigan. And it's important to motivate, again, why clinicians who may not be data science experts, why they should care. And the way I go about this when talking to different groups is just to underscore that machine learning, AI, is disrupting every industry. Healthcare isn't any different. These changes are coming, and the best thing that we can do is prepare for them. And just like just like interpreting or trusting or applying studies in a clinical journal, just like when we read a clinical journal article, that article demands that the reader has a basic literacy in statistics and study design. The same goes for machine learning. We need to start having conversations. You don't have to be an expert, but you should have some basic literacy in machine learning methods so that you could do the same thing when you read an article in your field's clinical journal. And then there's this point about balancing hype and hope that Brahmaji got into, I think is very important. You know, machine learning has been slow to permeate healthcare for good reasons. The main reason is that mistakes really matter. So, you know, if Facebook misclassifies your face as your twin brother, that's annoying, but it's not dangerous. And our culture, especially in healthcare, is very unaccepting of computer errors. They're much more accepting of errors made by a human. And so, you know, performance of a machine learning algorithm, if it's deployed in the clinical setting, has to be, you know, there's depending on the level of risk involved, there's a certain amount of performance, and for the high risk situations, the model may have to be very close to perfect. Being right isn't enough too. It's another issue we've come across is, you know, delivering the correct treatment or getting the right diagnosis isn't enough for clinicians. Then you need to have an understanding of the mechanism underpinning a specific treatment recommendation or diagnosis. We have to be justified in our decision making so that we can anticipate and mitigate against the next problem that a patient might have. And beyond that, there's, you know, this issue of data sharing, and the main, you know, there's data sharing. You know, there's the issue around sharing proprietary algorithms, but beyond that, in healthcare, it's you know, sharing of PHI that creates issues. So there's all these issues here that have caused machine learning techniques to be slowly adopted into healthcare. So now I'll go through some examples, including my own work and the work of others in anesthesiology. The first example I want to go through is a project that's been the start of a series of projects that's I've gotten NIH grant funding to do. And this is a project where we use perioperative data to detect heart failure in early stages, or I guess, you know, subclinical stages, and we you know, it's our hope that using perioperative data to detect heart failure potentially in early stages, we can have a potential referral system to a cardiologist who could potentially establish that diagnosis, get these patients started on treatments proven to improve mortality. So our goal in this project is, you know, the OR is one of the most well-monitored settings in all of healthcare. We're getting, when you know, not just the minute-to-minute physiologic data, but the waveform data, and it's a very well annotated data set too, meaning that whenever the anesthesiologist does something, gives a medication or a fluid, it's documented in real time. Our goal in this project was to use that anesthesia record as sort of a free stress test to elicit a potential signature, sort of what Mike Schoeding was alluding to with his ARDS talk, this digital signature of heart failure. We could use that stress test to elicit signs of early stage heart failure to be an early warning system for clinicians. And so what, you know, this project, it's using data both from the preoperative period. So if, you know, patient goes into pre-op clinic, it's a very well, you know, very detailed history and physical, and we get that data, and then interestingly, we get the intraoperative record, and we get that data that can be used as a free stress test to further inform a kind of a probabilistic algorithm for determining the patient's risk of having undiagnosed heart failure. So with each of these sets of data at two different time phases, we can compute the probability that a patient might have undiagnosed heart failure, and potentially have these patients reviewed by anesthesiologists and potentially referred to a cardiologist if the probability of having heart failure is high enough. And our cohort for this project is Michigan patients that didn't have a preoperative diagnosis of heart failure, and we defined, and so we split those up into patients that were healthy controls. They did not have heart failure diagnosed pre-op or within 2 years post-op, and then we had cases of patients developing heart failure within 2 years post-op. And then we carefully excluded cases from this cohort. Any patient that was undergoing a surgery potentially related to heart failure, like a cardiac surgery or an ICD implantation or pacemaker implantation, you know, we said that those patients, you know, they have a very, they were unlikely to have a undiagnosed heart failure, or they had, obviously, either by nature of their surgery, they have heart failure, or there's a low probability that they actually have undiagnosed heart failure. If having cardiac surgery, you got a very thorough workup. We also excluded patients that had heart failure acutely, that developed either as a consequence of the surgery or as a consequence of the acute surgical condition. A patient getting into a trauma patient coming into the ED in a motor vehicle accident, developing sepsis, septic shock, and then cardiogenic shock. We removed those types of patients. And so we're left with this cohort of patients who had chronic, potentially undiagnosed heart failure that was later diagnosed within 2 years post-op. And we wanted to see, was there a digital signature in the intraoperative record that could be picked up for these patients? And so what we had to do, and this gets into kind of the technical aspects of handling intraoperative data, with both with ICU data and other EHR data sources. It's very, very messy, and it's very challenging to come up with a way to cleanly segment the intraoperative record. But we had kind of a detailed kind of hierarchy algorithm that split the intraoperative record into different time segments. And we had the time segment when the patient came to the OR. Then we had this time segment where the anesthesiologist was giving them medications to induce general anesthesia. And that obviously has an impact on their blood pressure and their hemodynamics. And we try to capture that with that time segment. Intubating the patient. So that's a very stressful, stress-inducing event. Although the patient's asleep at that point, their sympathetic nervous system is still activated and they're still responding to being intubated. And so there's a signature at that time as well. And then we looked at the signatures around incision. So again, the patient's under general anesthesia at this point, but before incision, at the time of incision, there's a stress response that's manifests as an increased heart rate or an increased blood pressure or an increased requirement for more anesthesia. So we have to capture all of that around the time of incision. And then there's this maintenance phase where the body has now kind of adjusted to the acute surgical intervention. The surgeon's working, and there's this maintenance phase of the general anesthetic. And then again, on the end of the surgery, there's this time where the surgery is basically done. The anesthesiologist has turned off all of the anesthetic agents that have been on for a while, and the patient starts to slowly wake up and then becomes extubated. And then after they're extubated, they're transported to the OR. So all of these segments could potentially have a digital signature. That's a subclinical signature that could help inform our probabilistic algorithm that determines the patient's likelihood of having undiagnosed heart failure. And so we took all of those segments, and within each of those segments, we looked at different data sources that were available in the OR. So your blood pressure, pulse ox, any physiologic value, ventilator data, fluids, transfusions, medications that the patient was receiving. And we captured all of that, and then we summarized those data points into different summary statistics for each segment. And through that combination of segments and values and summary statistics, we developed over 1,000 intraoperative features. We took the preoperative data, so the patient's comorbidities, demographic data, et cetera, and we combined that into an algorithm that was trained, and we developed different pretty just a simple off-the-shelf machine learning models support vector machines, random forest, and we looked at the performance of those models. And if you're interested in this project, you can take a look at the publication and read more about the methods and the techniques used. But one of the things I learned from doing this is that although the algorithm had reasonably good performance, it was limited by this low positive predictive value, meaning that the algorithm had an unacceptably high false positive rate to be clinically useful. And that's kind of a thorn in the side of any anesthesiologist, in that, our goal in the OR is to mitigate risk, prevent the rare but catastrophic events, or try to mitigate low likelihood events or uncommon diseases from worsening a patient's perioperative course. So the undiagnosed heart failure happens in a surgical population, roughly about 1 in every 200 cases or so, or I guess just to say, a new diagnosis of heart failure within 2 years after the surgery occurs about 1 in every, I think it's slightly less than 1 in every 200 cases. And so there's this issue that for a prediction model to be clinically actionable, it's either you got to have a higher baseline prevalence, or the model needs to be nearly perfect. And so, our next approach for this algorithm is beyond just having a high sensitivity screening algorithm. We would need to have we need to reduce the false positives and get a more specific confirmatory test, some lab value to confirm, to influence the likelihood that a patient might have heart failure, or actually get an echocardiogram to inform the diagnosis of heart failure. And so that's kind of the next logical step for this project. I want to go through a couple other examples too, because they highlight other issues that I've either come across or my colleagues have come across. Another interesting paper published 2 years ago in our field's lead journal is this algorithm that predicts hypotension based on a A-line waveform. And the goal is to just use an A-line waveform to predict hypotension, and you can do it 10 minutes prior to the event. You can kind of change that window to whatever you want. But some window that gives an anesthesiologist an opportunity to intervene. And since we can do things pretty quickly in the OR, 10 minutes is actually a reasonable time window to think about. And this algorithm, this wasn't my own work, but this is work out of UCLA, looking at both ICU patients and OR patients, and taking a couple different data sources and extracting features from an A-line waveform to predict hypotension. So there's a training, validation cohort, and external test set as well. The fun part of this whole study was that there are a ton of things. We have, when any patient that has an A-line, there is so much free subclinical data in that waveform that Kayvon was alluding to this earlier, that really hasn't been leveraged to any appreciable extent in clinical care. And things that we think about as clinicians is when A-line gives you a blood pressure, obviously, systolic, diastolic, and a mean. It gives you a heart rate, but it gives you all sorts of other interesting things. You can look at when a patient's ventilated, they have a change in their systolic blood pressure throughout the ventilatory cycle, and there's all sorts of subclinical features. And when you get down to it, you can actually extract about 3,000 different features from each beat of the A-line waveform. And if you take combinations of these features, you can come up with a feature set of close to 2 million features. And then obviously you're going to have to take a lot of steps to mitigate the risk of overfitting your model, but you have this immensely rich, very wide data sets of waveform features. And the team was able to take this set of waveform features and come up with a model that had a C statistic of kind of the mid nines, like 0.93, 0.94, for predicting hypotension within 10 minutes or 10 minutes from now. And so this graph just shows one example patient. where on the top you see their blood pressure. They define hypotension as a MAP less than 65. And you can see over time, the x-axis is time here. You can see on the top, the patient slowly has, a dwindling blood pressure, but then by, the end of this graph, you can see that they do become hypotensive. But the hypotension prediction index, which is the bottom figure, a scale from 0 to 100% certainty of hypotension, it rises pretty quickly right away to a nearly 100% certainty of having hypotension 10 minutes from now. So it is interesting how well this model performs. But the $1 million question is, can it actually prevent hypotension? And the $1 billion question is, can it actually improve outcomes? And it turns out that the answer is not obvious. A study earlier this spring in JAMA looked at this hypotension prediction index, which is now an FDA approved device, and has looked at it in a single center study where they randomized patients in the OR to having anesthesia care guided by this hypotension prediction index. And they did show a significant reduction in hypotensive events. In a study in our own, my own field's lead journal, about a month ago, they showed the opposite, that this hypotension prediction index, even if you give it to anesthesiologists in the OR for moderate to high risk non-cardiac surgical cases, it didn't actually reduce the incidence of hypotension. And so there's this issue of generalizability and testing your algorithm on different populations that's really important when you're developing a machine learning study. And this just really underscores it to have these two conflicting studies. So it is important. This validation issue comes up time and time again in machine learning. The other issue is, beyond what is actually, how clinicians are responding, and, reducing hypotension could theoretically be helpful. What are the unintended harms? And so there's plenty of, potential for, if clinicians are acting on a hypotension algorithm and they are giving medications that rapidly change the patient's blood pressure, that there could be unintended consequences. And so, this is something that is downstream from any of these models that are being developed, but is an important consideration, is that there is a process in place for the next step after you've created a model to actually be implemented in the real world. There's an FDA evaluation process that goes through different steps. It's to regulate how fast these devices enter the real world, this hypotension prediction index algorithm that's essentially software as a medical device. The FDA has recognized that the potential for harm hinges on both how significant the intervention was. So if you're just informing management versus actually treating a patient or diagnosing a disease. And it also depends on how serious the situation is too. So if you're developing a device that, predicts your clinic schedule, or how quickly you'll be able to get through your clinic schedule for the day, that's a little bit of a different context than a device that predicts impending hypotension or sepsis or ARDS or heart failure. And so there's these ranges that need to be considered, and the level of scrutiny that the FDA is going to apply to your software driven by a machine learning algorithm is going to be high or low depending on these conditions. And so this figure just shows exactly how scrutinizing the FDA would be, and the level for an independent review kind of somewhere in the middle here. And there's this iterative review process. I don't really want to get into too much of the details of this slide, but just suffice it to say, there's an iterative review process that the FDA will do for any machine learning algorithm developed as a software developed as a medical device. And so we need to be thinking about these downstream things as we're in the upstream phases working on machine learning based projects. And promoting this reality to clinicians that the FDA is approving different machine learning algorithms is helpful. Many clinicians are unaware of the sheer number of different FDA approved machine learning algorithms. It's since 2014, it's really taken off. Some of the ones that are very relevant to my own field are looking at the Apple Watch is a device that can be used to detect AFib in patients wearing the Apple Watch. There's chest X-ray analysis that Mike Shoding was alluding to in his own work, and a number of other different algorithms that might be useful for clinicians and anesthesiologists specifically. Next topic I want to go through is another project that my own team worked on, and getting at this idea that maybe the machine learning efforts, at least in the early stages, should be focused on the low risk setting, not the diagnosis of the critical illness or the life altering intervention, but rather the simpler, lower risk interventions. This project kind of took that to heart, and we used machine learning to improve our ability to just accurately bill for procedures. And so this is a study that our team developed and was published this past year, using machine learning to take anesthesia data and then determine and classify what billing code it should get. So it's helpful to do this quickly. Right now, when we do this, we have a billing specialist that takes on average over a month to do, and it's expensive and time consuming. And it's very much dependent on just reading free text within anesthesia records, knowing the surgical diagnosis and the surgical procedure text, which has tons of misspelling. So this is just one example. When we looked at any way that you can see a C-section entered into the anesthesia record, you get all sorts of misspellings and typos that make it, you can't just have some rule-based algorithm that computes whether this patient had a C-section or not. It has to be using this unstructured data with typos in it, and we need to use natural language processing to take that free text, and we combine that with information about the patient. So demographic data. So some surgeries you would not get if you're male versus female. So for instance, a C-section should probably not happen on a male. So that's useful information, the demographic data, your age, and there's certain pediatric procedures versus adult procedures. We took all of that data and we found it's really the natural language processing of the procedure text that has the most impact. But we found in a 17 center data set, we trained it on 16 of those centers, and then on a 17th center unseen by the algorithm, we could classify cases with a accuracy of 95 to 97% for the high confidence cases. And when I say high confidence, I mean we were able to compute a confidence level based on the most likely procedure code to the next most likely procedure code, and if that ratio was high, then we were more confident that we had the number one ranking procedure code was the correct procedure code. And we found for those cases, we had a very high classification accuracy, and we could do this in a second. We don't need the 33 days that a billing specialist might take to the lag time to have a billing specialist review these charts and provide these codes. So we kind of thinking through how do we deploy this, and we're doing this at the University of Michigan right now. Our anesthesia codes are largely built using a machine learning algorithm, but we wanted to figure out how to what's the role of the billing specialist versus the role of the machine learning algorithm. And we kind of embrace this idea that not all of this should be the algorithm, not all of this should be a human. And what we did was we split the cases by how confident we were, or how confident the machine learning algorithm was in classifying them. And so the figure on the left shows on that y-axis how confident the algorithm was that it had the right diagnosis code by looking at the most likely code versus the next most likely. If that ratio was high, it was very confident. And we looked at the the confidence parameters on the x-axis, and the y-axis is the accuracy of the algorithm. And so you can see for lower confidence cases, the accuracy is still pretty good, but not at the level of a billing specialist, which is historically 95% accurate. But for the high confidence cases, the machine learning algorithm is what we should be using. It does have higher confidence. It can perform actually better than a billing specialist as adjudicated by a clinician auditing billing codes. And so, so we've split on the figure on the right. You can see the y-axis is the percent of cases that are included at different levels of confidence. And again, the x-axis is the confidence parameter again, but we can see that for cases that have a lower confidence, we would still rely upon a billing specialist, and that's about just over 40% of the cases, and the remaining 55% or so of cases are using the machine learning algorithm. And so that's one practical, much lower risk application of machine learning. That's kind of the lesson, or the kind of the thought process we had in developing this algorithm is starting with maybe lower risk health applications rather than targeting the high risk. Although more interesting applications, maybe the lower risk ones are the low hanging fruit for which we can focus our machine learning efforts, at least in the earlier stages. I'll go through, I'm just trying to see how much time I have. Maybe one more algorithm I think is pretty interesting, and this is work again by the University of Michigan. This is not my own work, but this is work that Resea is involved in. I think, I can't remember if Mike showing it. Yeah, Mike has been involved in this work as well, and this is just a preliminary work, and Mike Sheridan can jump in too if I misrepresent anything here, but I think it is an interesting paper and kind of goes through a couple. I think there's some interesting principles that we have to think about when using this for clinical care. But it's an algorithm that predicts a patient deteriorating in the ICU. Deterioration, or I guess an algorithm that predicts a patient deteriorating and needing either ICU level care, an ICU transfer, needing mechanical ventilation, or the patient died. And the goal of this is to study the performance of a algorithm for detecting patient deterioration. This cohort was patients with COVID admitted to a non-ICU setting, and the data collected was just routine data that is generally available on most hospital inpatients, and this included physiologic data, also nursing assessments, and lab values. And the model output was a score of 0 to 100, representing the likelihood of deterioration. The algorithm had some modest performance, not perfect, but certainly useful. But I think the interesting part of all of this is, if you're going to have a conversation with a clinician that is looking at this algorithm, they're going to want to know how it works, why we should trust it, and what should we even do with this information. And it gets at this notion that, at a minimum, the model has to be accurate, but that's only a starting point. That's the theme that Resea, Kayvon, Mike have all stressed in their own talks, and that accuracy is important, but there's many different layers for a model to be trustworthy, or there's many different layers that need to be addressed for a model to be trustworthy and useful for clinicians. So it needs to be accurate. It needs to be transparent too. So the clinician needs to understand what factors are driving the prediction model, and mechanisms are important. So just like there's many different causes of low blood pressure or hypoxia, and they imply different treatments, the same is true for a prediction model, right? So if a patient's respiratory rate is driving the prediction, it's a little bit different than a lab value or some other vital sign driving the prediction, and they have different implications for a clinician that's trying to interpret this model. The model needs to be credible, and Kayvon alluded to this in his talk to some extent, but basically, does the model do the variables or do the features in the model that are driving a prediction fall in line with expert opinion, or are they in contrast to potentially decades of literature on a particular topic? And certainly experts can be wrong, but that's uncommon. And for a model to be credible, it needs to be influenced by features that offer a plausible mechanism underpinning the association between the prediction and the outcome. And so, for example, if the deterioration model hinged on a patient's age and vital signs and blood gases, that is more credible than a model that seems to be driven by the day of the week or the patient's height. And that's not to say that useful inferences can't be made based on the time of day or the patient's height. They just tend to carry less weight than factors that a critical care physician like Mike Schoeding has come to trust through decades of established research and teaching. And then at the pinnacle of all of this is whether a model is actionable or at least informed by modifiable risk factors that imply specific treatments. So it's one thing to build, to have a model that's built on age, race, and gender. It's another thing if it's built on variables that can be modified in real time, like blood pressure, oxygen levels, hematocrit, and these are variables that can plausibly be tied to interventions, so that at least there's a potential to inform treatment decisions beyond just risk stratifying. And so taking into all of taking into account these principles of transparency, of credibility, of actionability, we can take a look at the EPIC deterioration index. So this is a way that that the electronic health record, in EPIC, attempts to kind of visualize and convey that what's underpinning the model to a clinician who, again, might have a very low level understanding of machine learning. So in this example, not only do we get on the left-hand side, that 41.9%, we not only get a probability of deterioration, but we also get transparency. So we get to see what characteristics are driving this machine learning model. We get some credibility in understanding how important the variables are to the model. And so it's interesting to see that age and respiratory rate are driving the deterioration index, and that makes sense. A critical care physician would believe that. And it also embraces actionability, at least to some extent, in that some of the features in this model are modifiable. So we could do things to improve the patient's oxygen saturation or blood pressure or sodium levels or pulse rate. And again, these machine learning models, they're not causal inferences, but they're at least driven by potentially modifiable risk factors. So that improves the ability for the model to be actionable. So this isn't a panacea, but by showing what's under the hood, the EPIC deterioration index is a lot closer to earning clinicians' trust than just displaying some magical black box risk score. And I think that's really helpful. I'm just going to finish here. There's just one slide on bias. You'll note that two components of that deterioration outcome were clinician behaviors. So there was the ICU transfer and the start of mechanical ventilation, and so the algorithm was modeled by clinician behavior rather than just characteristics inherent to the patient. And that can be, and so when a machine learning algorithm learns to predict a clinician action, it's also learning the biases of those clinicians taking that action, which could be good, but it could also be bad. And one recent example of that is a gender-biased hiring tool that Amazon now had to stop. And maybe you guys are familiar with the story, but very briefly, it's an algorithm that took resumes for potential hires at Amazon and applied a machine learning algorithm to determine the likelihood of them being a suitable hire based on what the history of which candidates they had hired in the past. And they found that the algorithm reflected their own human biases in having males be more likely to be hired than females, and so they had to discard that. And the algorithm was certainly flawed. And it's interesting, and it allows for some introspection of our own biases. And so that's important. So when we're designing these machine learning algorithms, are we designing them based on behaviors or based on specific characteristics of a patient or healthcare delivery? So that's a very important consideration. So take home points. Machine learning for perioperative care is conceptually feasible. The next steps are to focus on ways to improve trust, that these algorithms could be generalizable, that they're safe. We're aware of our biases in the algorithms and that they can be clinically actionable. So things that, I think that we all need to consider as we go down this road is, promoting literacy. So again, going at this idea of making sure that clinicians who are reading, papers in machine learning methods have some basic literacy in machine learning, but also meeting them where they're at and having the writing of a journal article especially a clinical journal be written in a way that a clinician can understand. And so there's a lot of technical jargon that we need to think about how we're going to write it in a way that's accessible to clinicians. We need to focus on the right problems. So again, there's this trade-off between the severity, and the implications of the model versus, and which ones are suitable for a machine learning model to solve, and the FDA implications there. We need to make sure we're focusing on the right inputs. It's this idea of what's driving a prediction model and the transparency, credibility, actionability. And then we need to learn our biases. So we need to learn how biases in our own behaviors might impact a machine learning model. And so those are all things, they're like I said, this talk isn't necessarily about successes or the deep content of my own work. It's just about kind of the lessons I've learned along the way and things that I think we need to think about if you're going to go down the path of using machine learning in your own clinical work. So I will stop there, and maybe we can open the floor for questions, both for my talk and Mike Schoding's talk.
Excellent. Thank you very much, Mike. Again, we learn from these talks a lot more than reading 50 books on using biomedical informatics and stuff like that. This is the way that people who have gone through the process can explain the challenges and opportunities. So if you have questions, please raise your hand, and James will give you activate your mic, basically. And we would like this training. Okay, Christopher, yeah. You saw that?
I did, yeah. Christopher, you could re-raise your hand. It brings you to the top. There we go. All right, Christopher, you can unmute your mic.
That was actually an accident, but I thank you for giving your talks. They were great. I've had a great day learning, so thank you.
Awesome. All right, David.
So that I thought both examples were awesome, but in all seriousness, the billing thing really caught my attention. When is that going to roll out to everybody? Because I would love to not have to click on things to bill. In all seriousness.
Yeah. I think he's that. It's the project that in our department has caught on the quickest, and again, it's because of the fact that it is, there's certainly important implications, but it is a much lower, it's a, on that FDA, kind of risk grading table, it kind of falls into the, the safe corner. And so it was, more quickly endorsed by our department. I guess I don't have I don't know if Mike, if you have thoughts about how, if this is going to catch on with other administrative data, but it's at least caught on at the University of Michigan.
Well, I think, it illustrates an important general point about data science and medicine, and finding the sweet spot of what's the right clinical problem to tackle with machine learning is an open sort of question. We want machine learning to help us with these really hard problems that are really high risk, or do we want machine learning to help us with sort of mundane tasks that we don't want to do anymore anyway? And so I love this example because it really shows the power of machine learning for these sort of potentially mundane tasks, but ultimately can have a lot of impact. So you know, I think just like with any type of clinical research that you set out to do, people have a lot of sort of ideas at the outset, but ultimately, you know, many of those ideas sort of fail as you sort of think through them and as you get feedback from them. And I think it's the same thing for lots of machine learning problems. You know, like I worked on ARDS, it's a hard problem. It's potentially a high risk problem. You know, the CPT codes it's a great problem too. So it just illustrates the sort of the breadth of potential applications that this can have.
Perfect. Awanti, I'll unmute you.
Yeah. Hi. Thank you so much for this really, really wonderful talk. I learned a lot in today's session. I guess my question is more of when we're using EHR data, right, for any clinical problems, or just trying to use machine learning on this data, is there like a general way to go about cleaning data, or like what? Because sometimes you're totally dependent on the clinicians who've entered the data, right, over time. And if you're looking at records, sometimes there's a lot of missing data, or sometimes some fields, you know, they may have mixed variables, like it's not just a simple yes, no, categorical output. So I think that really affects your model. So I don't know, my sort of question is, how do you approach this? Like, do you look at particular cutoffs, or like, do you look at, you know, trying to make sense of all the missing information or cleaning as?
Yeah, that's a great question. I'll let Mike Shorting first talk about Fiddle. I'm reminded of Fiddle right now. And then I can show you a tool that our own department, our University of Michigan, has put together that addresses this question too.
Hold on one sec.
Yeah, I'm trying to do the same thing. I'm trying to bring up our own program.
Yeah, so this is a really interesting challenge. The use of electronic health record data brings a lot of challenges, and I would say that this is potentially a space where you know, advancements can be made in data science for all these reasons that you allude to. There's a lot of missing data in electronic health records. That missing data is not missing at random, you know, to use a statistical concept. Like, there's probably a reason why the data is missing that may or may not be related to a particular unmeasured characteristic of the patient. There's a lot of different data types, and it's hard. So we have worked on this, sort of pre-processing of data with, and so Fiddle is a pre-processing tool that we published that describes a principled way of analyzing complex electronic health record data. And I think this is a reasonable starting point for people who don't have a lot of clinical expertise. But I would say that there really isn't a substitute for you know, thoughtful collaborations between someone with clinical expertise and someone with technical expertise. Even if that clinician, you know, doesn't know the ins and outs of algorithms, they could at least tell you why this particular variable in the EHR data is completely biased and should not be used.
Yeah. Oh, this is awesome. I'll definitely check out this paper of yours. Thank you so much. And I agree with you. Like, yeah, having that domain expertise would definitely help. Yeah.
Yeah. I agree with all of that. I just want to show you another approach to handling, you know, the messiness of electronic health data that our anesthesia department has focused on. And it's this idea that, you know, any one raw data source can be has a certain amount of noise and there's biases and issues with any one data source. And but you know, if you but you know, the clinical questions, the questions that a clinician is trying to answer, and the data that they're looking for is often the same across different projects. And so our own anesthesia department, for as a tool to help clinicians get better quality data. We have this tool called the phenotype browser. And basically what it does is it takes different types of data that I show here, fluids given to a patient, medications, vital signs, diagnoses that they have, and it puts it through kind of a logic circuit that is a rule-based algorithm that combines multiple sources of EHR data that all have their own limitations. And it takes, it logically applies specific rules to have a higher level clinically meaningful inference that you can derive from them. And so, the example that I love to mention, just because I'm a cardiac anesthesiologist and I think about cardiopulmonary bypass all the time, is exactly that. Is how do we, in an anesthesia record, represent cardiopulmonary bypass? And there's a bunch of different ways that we represent it. One, we turn the ventilator off. So if the respiratory rate of the patient is 0, that's one way that you can represent. You have that influences the probability that the patient is on cardiopulmonary bypass. It's not a for sure. If their pulse pressure, the difference between their systolic and diastolic blood pressure is 0, that's another factor that influences the patient's probability of being on cardiopulmonary bypass. If their heart rate is 0. And so there's a number of different things that you can use. And if you combine different raw sources of messy data, you can have these higher level phenotypes that are still not perfect, but you're going from 90% accurate to 99% accurate. And that might be the threshold for doing a research project and having a much more reliable data set. And what we've done is we've taken these phenotypes and we now have made them publicly available on our website to researchers that can use these as Lego building blocks to build different research projects. And we see that they get used time and time again, and you're not going to, reinvent the wheel each time you want to do this project. You can use, the same phenotype, and it also helps with reproducibility. So you can make, the way you've done, a specific study is now comparable to another study if you use the same phenotypes. So that's how we've gone about doing it within the anesthesia department.
Oh, that's could you share a link to this website, or is it again?
Yeah, sure.
I would just say that the pre-processing aspects of data in these types of analysis are really, there's so many decisions that can be made. And so sort of having more consensus about standard approaches for pre-processing electronic health record data, I think would really help the field in terms of reproducibility. So I think, using standardized approaches as much as possible, I think would be really valuable.
I just put a link into our phenotype browser that has these different higher level inferences, but it's, the standardized methods for cleaning data and making them accessible to clinicians who may or may not be data scientists is really important.
Any other questions from the participants? If not, I would like to thank Mike Shoding and Mike Mattis once again for the wonderful job, wonderful presentations that they did. James, we're going to have a break until 2:45. Is that what it is?
I believe so. Yeah, I think even with some of the adjustments we made, I think we can get a 10-minute break in here.
Okay, so we'll be back in about 10 minutes.
All right. See everyone soon.
Thanks, guys.
All right, fantastic. So what we're going to do is go over the details of what's coming after that. Workshop is practically over. We have, a networking session after that for, more Q&A and talking about the strategy. But I'm just going to tell you a little bit about what is happening after the workshop. So phase 2 is a boot camp, which is happening sometime during this summer 2021. I don't know exactly when, but this is the tentative, schedule for that. On Monday, we'll start with, just welcome and introduction and talking a little bit about data science and artificial intelligence. but then we will have 2 sessions that are both dedicated to fundamentals of the mathematical foundations. You need to understand all those techniques. We will have 2 sessions. Don't worry about the math. We make it as easy as it can be in order for people to understand have some intuitive understanding about the concepts without getting into too much detail. And then we start with talking about what is classification, what is clustering, and that's the first session of machine learning. We talk about certain clustering technique, and immediately in the afternoon we have a session in introduction to Python programming, which we talk about the basics of programming with Python. That's the first day. On Tuesday, we talk about some fundamental classification techniques. We start with linear regression, logistic regression, lasso regression, those kind of techniques. Then we talk about more machine learning techniques, simple machine learning techniques like naive Bayes, and we talk about how to reduce the feature space. Then we talk about how to validate and truly assess the models. And this is probably the most important session of this. We want to make sure that we are not playing with just overfitting the data. Then we will have one scenario, one of the experts that we talked with Michael Shoding today with Michael Mattis. Mike Shoding, Mike Mattis, Nambi Narasamy, and Matt Davis. These are the people who give 4 talks in which they describe how to use these techniques that we're covering into their different applications, clinical applications. So it would be like the talk that we had, the 2 talks that we had today by both Michaels, but this time they actually go into more details about the technical methodologies and the mentality that then went behind these projects. So we have 4 of them. Tuesday we will have first of the 4. Then in the afternoon again we will have Python programming, in which we practice using the methodologies that we discussed in the morning, the same methodologies, but we practice coding them in Python, and we use real-world data. We talk about a couple of a few databases, and we play with these medical databases, and we run different machine learning algorithms on the data. Then on the 3rd day, on Wednesday, we continue with artificial neural network, and we talk a little bit about the regression trees and some fuzzy methods. Also, we talk about random forest. Then we have the second of the 4 presentations on how to use, actual usage of machine learning in clinical applications. Then in the afternoon, again, we use Python programming for implementing all of that. Then on Thursday, we continue having, neural network, different types of machine learning, support vector machine, and some agent-based modeling. Then we had 2 sessions dedicated to basically implementing these methods in Python. Thursday, we continue. Friday, we continue on essentially, we covered most of the machine learning. Now it's time to talk about the strategy, how to incorporate data science into competitive grant proposals. We discuss about how to properly use these ideas when we're writing grant proposals in biosciences. Then we have another one of these clinical talks and using machine learning for clinical applications, and yet another one, the last one. In the afternoon of the last day, we have basically 2 sessions. One, we talk about some guidelines, how to use machine learning and data science for clinical applications. We go over the details on what Mike Mattis was talking about. If you're developing an algorithm, what are the specific guidelines you have to follow for FDA approval, for using, making sure that there's no bias in the data or the algorithm, and those kind of guidelines. There aren't very specific guidelines, but there are some good practices that we will present it in the workshop. Then the last session is essentially wrap up and talking about the next stage, the stage 3 of the training, which is the follow-up meetings in fall of 2021. So before I talk a little bit about follow-up in fall of 2021, I want to tell you that there are many other resources across the campus for things not exactly data science as we discussed, but similar applications. For instance, there is a master degree in clinical research design and statistical analysis that Mike Schoding mentioned that briefly. And this is, I have put a link in there. This is mainly for people who want to know some basic statistics and focus on applications like epidemiology and some statistical analysis of clinical trials and things like that, some understanding on that side. It's not what we are doing in this, but it's also relevant. People may benefit a lot from this program. But remember, this is a master degree. This is far longer and more comprehensive than a 1-week bootcamp that we do. And then there is a whole lot of workshops that CSCAR, Consulting for Statistics, Computing, and Analytics Research, CSCAR provides, and I have a link over there, and they have different, every couple of weeks or every month, they have a talk and mini workshops that they talk about specific applications of data science, for example, how to do video analysis on this type of data and so on and so forth, and they're very, very helpful. And I think, everybody can benefit from attending that. And they also put a lot of emphasis on the statistical methods and some machine learning. So there are a whole lot of resources that they have small amount of overlap with what we're doing. They're not exactly what we're doing, but at the same time, I think people can benefit a lot from these resources together with the workshop, with the training. Now, let's talk about after bootcamp, what happens as the follow-up. We would like to have monthly meeting. We haven't finalized that. We would like to have monthly meeting during the following fall. Like, in summer, we do the bootcamp, and in fall, we stop the workshop. And the reason behind that, like I mentioned at the beginning of the workshop, is because I looked at a number of trainings, not here, everywhere, that people take the classes and like they go through intensive training, but when it's over, it's practically over. Nobody is using these things. Nobody is helping participants to see how they can monitor them, to see how they're actually using these techniques and help them, essentially apply the knowledge that they have gained in the workshop, in the training. We want to avoid that. We want to make sure that there is a continuation to what we're doing in bootcamp. As a result, we want to basically meet with participants and see what challenges they're facing, what they have achieved. Is there any way we can help them? In particular, I'm assuming that a number of people getting into this are the early career people, junior faculty, early career researchers who want to get like a K grant or the first grant or something. And I think we will be able to help these people, by sort of giving some advice and going through like the work that they're doing to improve the proposals and increase the competitiveness of their work. This is not something like what Mishar is doing. Mishar is actually forms a panel and gives you feedback or something. That's not going to be the case. We don't want to write the proposal for you or give you feedback on every aspect of that. We just want to see how you plan to integrate data science into your proposal and help you do that. That's the only part that we want to do. We want to make sure that there is a good integration of data science and the biomedical clinical research that you're planning to do, and we help you improve that. And we put you in contact, depending on the project that you're doing, we would love to put you in contact with people with a specific expertise in data sciences who can help you in the future. And the people whose expertise would complement what you're doing might be good partner, good, data science to collaborate with. We want to form some sort of matchmaking role for this process to help make your project have a higher impact in the future. So that's what I wanted to cover. We can have a Q&A now to answer the question, or anytime you're ready, we can go to that Remo that James has created for us, and the link is on the system, and basically start doing the interaction over Remo with the rooms that James discussed. Let's see if there are questions. If there are questions, I'll be happy to answer them now. Otherwise, we can go to Remo.